about this. And I've been doing this now for about 10 years. Just kind of look around the room. You're going to see folks that are really interested in this topic. And as this quantum explosion we're going to be seeing over the next few years, you're the original, you're the OGs of quantum. So thank you all for coming with us. I definitely want to thank Carasoft, Craig Abod, Mary Martin, Brian O'Donnell, and Troy Murrah of Carasoft for letting us use this facility. It really helps stretch our programs. And what we found out during COVID, what we used to do all our events downtown DC. A lot of us don't live in downtown DC. So a lot of federal folks don't live in downtown DC. And if they can avoid going downtown DC, they're going to do it. Also want to thank Carasoft for the great weather today. It's all, no rain or anything. So just real excited about this program. I want to thank our partners. If we can put that slide up, or do I have to move it? Okay. Yeah, we've got some great partners here, media partners, and some of these early companies that are in it. I definitely want to do a special shout out to Allison Schwartz at D-Wave and her team. Allison was instrumental in starting our quantum working group, which has been going strong and building momentum in these early days of quantum. So anyway, ATARC, we're the Advanced Technology Academic Research Center organization that facilitates collaborations such as these with government, industry, and academia. So we're going to roll right into it. Our first keynote speaker is Dr. Yakov Weinstein, who's the Chief Scientist of Quantum Technologies at MITRE. Can we get Dr. Weinstein? There you go. Okay. Yeah.
All right. Okay, great. So thank you all so much. Thank you for coming. Thank you for this opportunity. It's really an honor and a privilege to be with you all and to open this first, hopefully annual for many, many years, ATARC Summit. Again, my name is Yakov Weinstein. I'm the Chief Scientist for Quantum Technologies at the MITRE Corporation, which is based over in McLean, which is not too far, but I'm actually based in New Jersey, so I had to drive yesterday. But really, it's great to be here. And my goal for this talk is to convince you that what we are doing here is a quest. This is a quest for humanity to harness the power of quantum. That's our goal, right? We are not simply looking to improve quantum technologies. We all want to do that. We have wonderful industry partners here. We have wonderful academics here who are concentrating on improving technology. But our goal is to harness quantum phenomenon to use them for the betterment of humanity. And that requires more than simply advancing technology. It requires a quantum workforce. It requires companies. It requires having people who can teach. That's what we're trying to do. And if we think about it, the goal of humanity to be able to harness natural phenomenon for its own good has gone on in many different areas. If we think, for example, sometimes we've done it successfully, sometimes we've done it less successfully. So let's take an example, right? If you think about nuclear physics, we talk about nuclear forces. My PhD is in nuclear sciences and engineering at MIT, so whatever. In theory, that's what I do. So if you think about it, we've been somewhat successful. We have nuclear bombs. We can argue whether that's success or not. We have nuclear power plants. But we don't have, for example, nuclear devices, right? So I hope everybody's read Isaac Asimov's Foundation trilogy. Can I assign homework, by the way? Okay, if you haven't read it, by next year, you should all have read Isaac Asimov's. Anyway, so if you read through, though, he assumes that there will be nuclear devices that everyone will be able to have in their pocket, right? And that's a realistic assumption, in a sense, because if you can really control nuclear phenomenon properly, then we would have such devices. But we, as in humanity, has not attained that level of control of nuclear phenomenon to this point. If, however, we look at electricity, we all have, I'm holding two electric things, right, in my hand, and I've got one in my pocket, maybe more than one. And we've been extremely successful in harnessing electricity, right? What did that take? What was necessary in order to do that? Well, let's think about it. From the lightning rod in the 1750s to the light bulb, let's say 1770s, 1780s, was more than 100 years. Sorry, 1870s, 1880s, right? More than 100 years. To go from that then to, let's say, vacuum tubes and transistors, a little bit less than 100 years. I had an undergraduate professor, Professor Taub, a really interesting guy, was at least 85 by the time I had him, had a full career, and he told me in an advanced lab that he was gonna give us a chapter from his book, which he had written, 30 years before, and he on transistors, because we were gonna do transistors in the next lab. And he said, yeah, transistors had just come out, and we weren't sure whether this was like some sort of passing fad or whether they would catch on. So the last minute, we decided we'd put a chapter in our book about transistors, and we were all like just agape, trying to what are you talking about? How old are you actually? But that was part of the quest. It was part of learning how to harness electric, the phenomenon of electricity. And that's what we want for quantum. So it is true that we want to be able to build quantum computers and quantum networks and so on and so forth. But if we really want this quest to work, we need to produce not only the companies, we need a workforce, we need quantum technicians, right? We need all of those people in parallel to what we have now in the field of electricity. So here's a question here. Is quantum different? Is it somehow different than electricity? Or is it different than nuclear phenomena? Or is it different than magnetism? And I'm not sure what the answer is. But the answer, like if this was a conventional computer, a quantum computer, I'd have no problem with it. But because it's conventional, anyway, so maybe the answer is yes. I don't know. But I'd like you to think about it. There's a lot of investment currently in quantum. There is a lot of excitement about quantum. There's a lot of hype about quantum. And there's a lot of expectations about quantum. Billions of dollars, trillions of dollars. I know you look at the McKinsey reports, you look at other reports. I can't even count that many zeros that they're putting at the end of what the quantum market is going to be. But can we deliver on that pressure that is upon us? And I don't know. I don't know if Edison had the same pressures. I don't know if the Wright brothers had the same pressures. Did they feel that this needed to be done because if we don't, then all of the investment that's been put into flying machines and been put into electricity will be a waste? Maybe, maybe not. I would be interested to know if anybody actually has the answer to that. But what I do know is what's going on now, which is that there is a lot of expectation and there is a lot of pressure. And if there's not a return on investment after a certain amount of time, people are going to pull their funding. So what do we do? Right? How can we make sure we're successful in a time period that's relatively short compared to the hundreds of years it took for electricity to really come out to its own and come up with electric devices? So this is what I like to call the quantum ecosphere virtue cycle. And my hypothesis is that if we can get this virtue cycle to work, then we can be successful. But it requires communication. That's what we're doing here. So let's take a look at what I'm going to call for the moment, and I'm sure I've left lots of things out. I'm going to add a few in as we go on. But three corners of this triangle. We have academia, we have government, and we have industry. Each one of these institutions has certain needs and certain desires. And if they all work together, everything will flow beautifully. Okay, so let's figure out how that is. Okay, what does academia need? Well, academia needs a few things. They need research dollars in order to be able to come up with the brilliant ideas that they come up with. They need an educated workforce. They need educated secondary schools, right? To make sure that they have students who can work with them in order to achieve those goals. And those are provided by the other branches. So that's what they need. And what they produce is ideas. And they produce an educated workforce. Okay? Government needs an educated workforce. Government needs to be able to protect its citizens, so they need various things that will help them do that. Government needs devices, and all that is provided by academia and by industry. Industry needs ideas. Industry needs a workforce. Industry needs to be able to sell their products. Government provides a customer. Government provides, in some cases, funding. Academia provides this workforce, and if all that works, then everything will move forward as we expect. However, there are bottlenecks. And we need to identify those bottlenecks and try to figure out how to circumvent them. So what are some of the bottlenecks? So academia wants to publish, right? Publish or perish. Wonderful. However, government or industry may not really want that, because government and industry, understandably, this is not in any way to be critical of any part of these people or of academia, but there's a bottleneck. Government doesn't want certain information to get out into international hands. Industry wants to make sure that it protects its IP. Okay? So that pressure from academia is going to be pushed back on from industry and from government. Right? Government, that's one bottleneck, right? Industry wants to make sure it can increase its sales. Industry wants to make sure that its IP is protected. Right? Industry wants to also sell internationally, right? Which government may not be so happy with. Right? And the government, itself wants to keep things protected. They want the ideas, but they don't necessarily want everything to be announced. They want to be able to provide a job market for its citizens, but they also want to make sure they can protect its citizens. And so how do we get around these bottlenecks when academia, industry, and government all have different goals? Academia wants to know what's publishable in very, obviously I'm stereotyping a little bit, and I'm also not going into details, but academia wants to publish, industry wants to be profitable, and the government wants to know what it can use. So what do we do? So the truth is that there are certain organizations that are already set up to try to solve these problems, and that's what we're doing here. Right? So as an example, and this is not comprehensive, but there are, for example, national laboratories. Right? National laboratories are part of government, but they work very much in the academic sphere. And so they go to the same conferences and they talk to each other and all those things, but they also talk to government. Okay? We have, between industry and government, we have wonderful organizations like ATARC and others who try to put people in the same room so they can talk to each other, they can learn from each other, so they can understand the desires and the needs of each one. And between academia and industry, we have things like industry postdocs, we have STTRs, we have industry fellowships, and so on and so forth, right? All in order to try industry to be able to take advantage of what's going on in academia, and academia to be able to place its students in jobs that are beneficial for them. So those are examples of how we get around some of the bottlenecks. And then we have organizations, I'm from MITRE, so I've talked about MITRE, that try to work with all three, like the MITRE Corporation, other FFRDCs, Quantum Economic Development Consortium, other economic development consortiums like Connected DMV here in the Washington area. Right? The goal of all of these organizations is to ensure that people can talk to each other, to get on the same page. And what I'd like to urge all of us today to do is to be aware of everyone's needs, right? Outline goals and expectations as you set up partnerships, and try to figure out kind of roadmaps and timelines so everybody's expectations can be met according to what they desire. And that then brings us to practicing quantum. We are on this quest. We are not finished. We are not even close. How do we move forward? Not from a communication standpoint, that's obviously necessary, but also what should we do? And so these are my ideas. These are not necessarily the right ideas, it's just my thoughts. But as an example, start with quantum sensors. They're generally easier, less things to control, less phenomena needed to be exploited. Things like atomic clocks have been around for decades, so there's already, as it were, a track record for different quantum sensors. And there are other quantum sensors like nitrogen vacancy sensors, as magnetometers, Rydberg electric field sensors, and so on and so forth. And that's something that we're concentrating on a lot at MITRE. We have two major quantum sensing efforts, one in nitrogen vacancy sensors to use them to scan integrated circuits to look for faults, and one on Rydberg sensors for ultra-wideband spectrum situational awareness. So that's a way of practicing quantum, and something that we expect to mature over the next few years as opposed to the next few decades, though I am not going to get into that argument. Number two, to look at our current NISQ systems, right? Be it the systems, the universal systems coming out of Quantinuum, IonQ, and so on and so forth, be it the annealers that are coming out of D-Wave, right? Look at our current quantum computing capabilities and ask, is there something practically useful that can be done. Okay? And this is, again, going to require communications. It requires spanning the field of all human problems to figure out, is there one or two that that can benefit from our current systems? At MITRE, we're taking a little tiny piece. We're looking at synthetic data generation for images based on quantum computers. Is that going to work? I don't know. It might not. I'm not sure it's necessarily better than any other problem that people may have in mind. But but it's fun, and we have the government paying for it. So hey, that's great. But in addition, we need to learn to control quantum systems. And this, David Corey, who is currently at Waterloo, but was at MIT when I was a graduate student, he was my PhD advisor. He told me 25 years ago, he told me, what we are doing is learning to control quantum systems. Anything else that we put out, and certainly anything that we put out 25 years ago, looking at liquid state NMR, everybody remember liquid state NMR? Anybody have any idea what that is? Okay, I do like another homework assignment? Okay, when you get a chance, you go into the archive, if those papers still exist, they haven't gotten rid of them, but look at liquid state NMR quantum computing. And one of the points that David made was that there is nothing that we are doing that is actually going to be useful to building a quantum computer. A full-blown quantum computer will not use liquid state NMR. But we're learning to control quantum systems. And some of those control techniques are still used today, many years and many stages of quantum computers later. Control. And then, finally, we need a way to keep score. We need to make sure that there's a track and a track record of progress or not. And that requires having metrics. Have our quantum computers improved? Have they not improved? Are quantum networks better? Are they not better? We don't know quantitatively unless we have numbers that we can attach to these technologies. And so that is something else that I would like to put out there. There are some metrics out there for quantum computers. There are some you can kind of make up for quantum networks. But knowing where we are, being able to communicate how we've moved forward, both to government, to industry, to academia, to the public at large. This is where we were 10 years ago. This is where we are today. This is what it means. If we can do that in one paragraph, we've won. Right? We've all won, because we can keep moving the quest forward. If we can't, and all we say is, and I'm not saying that anybody here or anybody elsewhere says this, we say, oh, look, we have a more powerful quantum computer than we did 5 years ago, or, oh, look, we have 4 nodes instead of 3, not gonna work. No one's gonna believe us. Right? No one's gonna take it seriously. We need to be more blunt, more hardcore, and clearly delineate what we've been doing. And so, to end, these are the tracks we can take. We can look at this entire ordeal as trying to improve technology. That's wonderful. We can say, oh, there was an ENIAC, how many years ago? 80 years ago. And we've gone from there to desktops, to laptops, to smartphones, and we're going to do the same thing for quantum computers or our quantum systems. Okay, then someone will build a quantum computer, and that'll be great. Or we could take the much more majestic approach, which is to realize that our goal here is to harness powers of nature, and that we are, in our quest for quantum, following the footsteps of our ancestors who did the same thing with mechanics, electromagnetics, and everything else that we are so used to in our modern day life. And so I urge you, as we follow the red path rather than the yellow one, to understand that this is not necessarily a constantly ascending quest. There will be dips, there will be troubles, there will be bottlenecks that will get in our way. But that if we can go through them, and that we will be able to go through them as we communicate clearly with each other, then we can achieve control, complete control over quantum phenomenon, such that we will be able to build devices, computers, networks, ones that will fit in our pocket, that will exploit these natural phenomena for the betterment of humanity. And so with that, I would like to turn to all of you. You are being looked at today to lead this quest. to have those conversations, to be able to communicate with each other, to go onwards and upwards in harnessing quantum. Thank you. Oh,
Do we have any questions? Okay.
I ain't saying anything. I'm not quite sure.
Just state your name and agency.
I'm Kripa.
This is my mic. I'm like Jason Miller now. This is my mic.
DOC. So you mentioned that we are there where we were 10 years ago. Where the rest of the world, like our competitors like China or Russia on this
Okay.
platform?
Yeah, that's a really good question. So if we start now comparing what the U.S. is up to versus internationally, so I think this is important. This is an important question, especially from the government side. But because it's important for government, let me just put this into our into where we were. Because this is important for government, this should be important to industry as well, right? Industry should be sensitive to government needs. China is looked at as a near peer, whatever you want to call it, and therefore understanding where China is, for example. Versus, let's say, some of our closer allies, that is something that's important. Okay, so I think that it is going to depend somewhat on the technology itself, and we could go through details of every technology, but there's no question that China is moving forward, spending a lot of money. Certainly, if you look at papers that are coming out when it comes to quantum networks, quantum key distribution, anything in the quantum communications realm, so China is publishing much more than we are. And again, this is not to take away from any of the great work that's going on, for example, at Oak Ridge National Labs or anywhere else. But China is publishing a huge amount in that area, and presumably they have, and they released this in Nature in 2021 or 2022. Their quantum key distribution network, which goes from Shanghai to Beijing, and then is able to hook up with their satellites. So, from that perspective, I think it's clear that China is in the lead in that area, though I'm going to leave it to the experts in quantum networks to disagree with me, which is totally fine. When it comes to quantum computing, so U.S. industry, right, as represented here and others, is awesome. I mean, they're great, and they're doing wonderful things that 25 years ago when I was a graduate student, I would have never even imagined were possible. But U.S. industry is able to accomplish it, and it's not clear that China has been able to keep up with us. When it comes to quantum sensors, I say also, again, thanks very much to our industry, the US seems to be ahead. And those are, again, if you want to practice, I think, we're talking about practicing quantum. I am urging for the United States to practice quantum via quantum sensors. Right? Again, we're practicing controlling quantum systems, learning how to be able to manipulate them, learning how to be able to use them in ways that are beneficial to us. I am suggesting we do that, we, as in the United States, do that for quantum sensing. China has clearly decided to practice quantum via communications. I think that right now is the difference between us. And so they are pouring everything into quantum communications. It doesn't matter whether their satellite works or not. It's completely irrelevant, right? But they're learning to control quantum systems. That's what's important. And so, we can argue as to what the proper path is, but the need to practice to learn to control quantum, that I think remains primary in my mind. Not sure if that totally answered your question. But.
Hang on, let me get over here.
Yeah.
We got a lot of online folks too, so definitely have to use the mic.
Online questions, awesome.
Okay, I'll hold the mic just so you hear your name in it.
Thank you. One of my favorite movies is The Right Stuff, and there's a quote, "No bucks, no Buck Rogers." You being a trusted agent of the U.S. government, can you give us some insight into the budget, both government and elsewhere, that we're seeing for quantum?
Okay, so let me be careful, because I am not a member of the U.S. government. I work for MITRE, which is a not-for-profit FFRDC. So hopefully people regard what I have to say with some seriousness, but I do not in any way blame them if they don't. But in terms of budget, it seems, again, from the numbers that we can see, that the United States is not spending as much as China, for example. Again, with the CHIPS Plus Act and with hopefully the renewal of the National Quantum Initiative, or NQI, I think that's what it is. There'll be more funding for quantum. Yet our government versus the Chinese government, it doesn't seem that we are spending as much as they are. In addition, there are other countries, for example, in the EU, which seem to be outspending or close to outspending the United States. However, that does not take into account our industry. Again, I'm not going to speak for industry, any particular industry per se. You can ask the representatives who are here. But clearly, if you look at the size of the workforce of places like Google, Quantinuum, D-Wave, so on and so forth, industry is spending a lot of money in this area. our relationship in the United States, the relationship between government and industry is one way, and in China, it's a different way. So it's much easier to conflate industry and government in China than it is here. And so at the end of the day, if you're looking for like a bottom line number, I think it's really hard to tell. Because industry, understandably, I'm not blaming them at all, is not revealing the numbers, the amount of money that it's spending. So that was a good way to like kind of like circumvent your
I think
question.
one of our jobs is, and we have some lobbyists actually in the room, but our job is to educate Congress, as ATARC. I think we need to do a better job, and we're going to be spending a lot more activity like on the Hill, just so they're educated about this issue. Mark?
Mark Kagan, Panoptis Intelligence. Connecting to the dots that you put up there, one was trying to get the three sides of the triangle to cooperate with each other to advance things, and then you were mentioning about aviation and electricity. Well, in the history of the advancement of, say, aviation in history, you had a lot of fighting going on.
Absolutely.
Say
the Wright brothers trying to get everybody else out by taking all the patents. So yeah, I skipped that part.
Electricity between AC and DC
Absolutely.
and this kind of thing, and
Yeah.
it's always been the same with science and technology.
Yes.
Where is the not the competition, but the fighting, if you want, going on within quantum between the different theories and the different ways of going on between, you have thesis, antithesis, new thesis.
Yes.
Where is that
Synthesis.
going on? Because it isn't just always a matter of cooperation and reconciliation, and it isn't just a matter that we're competing with China because they're throwing more money and people into it. Where are the pieces of quantum development and quantum research that, we don't know where it's going to end up, and there are a lot of failures along the way.
Yes, absolutely. So again, it depends on exactly what technology you're talking about. But if we're going to either the quantum sensors or the quantum computers, and even the quantum networks as well, I guess it's really all of them. There is a question: what is the best platform? Are we looking at superconducting? Are we looking at ions? Are we looking at helium on electrons on helium, right? Or are there neutral atoms? There are a number of different ways to actually build quantum technologies, and exactly which one is going to be most successful, or whether it's going to be, as you said, like a synthesis between them, or different platforms end up better for different purposes. That I think is still very much an open question. I do want to say though that I've been personally in my involvement in QEDC, I've been like really. Maybe it's not my place to say, but I'm really proud of the fact that industries, and maybe people can correct me, but industry really seems to be getting along very well. And realizing that there is a benefit for all parties if we kind of raise the water level and raise all the boats. So as far as I can tell, and again, somebody from industry can correct me if I'm wrong, but we are not in the area of AC and DC where people are ready to shoot each other over it. Not even close. And we should never get there. But that question of what platform is going to be most successful between, let's say, a place like PsiQuantum or Xanadu that's doing photonics, a place like Google, IBM, D-Wave, they're doing superconducting qubits, and a place like IonQ or QEra, they're using atoms, that is very much still an open question. And I think that's where we're going to see the competition most strongly. Right now in the quantum computers, because that's what everybody's excited about, but the same argument is going to happen with the quantum sensors and with quantum networks as well.
Well, I think that's all the time we have. This is fantastic. I guess you're our inaugural keynote
Awesome.
of the entire
Thank
effort.
you.
Thank you. Appreciate it. One
Thank
more
you
round
all.
of applause. Next, we have Alexandra Kelly, who's going to be moderating the next panel. She's a tech reporter at NextGov FCW. Definitely follow her work. She's cutting edge. She covers the cutting edge issues. If you want to come up and bring your panel up, that'd be great.
Good morning. I didn't know I'd be standing in front of a mic. I thought I'd be sitting down, which is a little unfortunate for me. But I'd like to thank ATARC for organizing this event and for every speaker, for everyone who was able to show up so early to talk about such an intriguing yet complicated subject over breakfast. Okay, so our first panel is going to talk about demystifying quantum technology. Has anyone been able to do that yet? Yeah, I know, right? So our keynote speaker, our introductory speaker definitely helped us and walked us through it a little bit. But our panel here is really going to talk more about where we are in terms of public sector work, especially regarding the marriage of the principles of quantum physics into new technology, both in emerging systems and systems we use daily, like computers. So I guess I'll go ahead and introduce my wonderful panel, and everyone can come up and take a seat.
Sit down, we can make you sit
No, I'm
down.
good.
Yeah,
I'm
I
fine.
got it. I'm gonna
You
give you a
sure?
mic. Yeah, you're ready to roll.
All right, well, up on the stage now, we have Leonard Woody from Microsoft. He is the Director of Quantum Engagement. And following him is Miss Jessica Rosenberg, the Director of Education for Quantum Science and Engineering at the Quantum Science and Engineering Center at George Mason University. And not least either, Nicholas Peters, the section head of the Quantum Information Science section at Oak Ridge National Laboratory. And then joining us virtually will be Dr. Tara Fortier, the project leader for time and frequency at NIST. And I have no idea if she is online now or not.
I'm here. Can you hear me?
Oh, wow, yeah.
Okay.
Where are you?
I was hoping to be on that screen behind the other panelists, but otherwise I'm just a disembodied voice.
All right, this is gonna go great. Okay, so I have met my panelists already on a virtual call, other than Dr. Fortier here. But to give all of you a better idea of what they individually do, would we be able to go down the line and maybe introduce ourselves and talk about the work that we do individually with quantum technology?
Yeah, I'm Leonard Woody. I work with Microsoft through our quantum engagement and virtual field operations. So I meet with a lot of customers around how our Azure Quantum is our provider going forward. We also have a new product, Azure Quantum Elements, that gets into computational chemistry. And so we've been trying to work with national labs around that as well.
Rosenberg. I am a professor at George Mason University and Director of Education for Quantum Science and Engineering Center. And in that role, not only do I teach, but also we've been developing a lot of programs across sort of all ages and grades. We've been working on everything from K-12. We have a project working actually with elementary school teachers right now, as well as students and teachers more in sort of middle and high school. And then, of course, our university programs and developing everything up through a master's degree programs and beyond.
I'm Nick Peters from Oak Ridge National Lab. I'm an experimental physicist. I primarily deal with single photons and tangled photons, but we also have a lot of different experimental platforms, including ion traps, and in general, we do a lot of work in quantum computing and developing algorithms and trying to understand and benchmark quantum computers.
And Tara, wherever you are, could you tell us who you are and what you do at NIST?
Yes, no problem. My name is Dr. Tara Fortier. First of all, thank you for having me here. It's a pleasure to participate with all of you. So I'm a physicist at the National Institute of Standards and Technology. I work in the time and frequency division there, and I develop laser systems to interface with atomic clocks for the definition of time. Also, we work a lot on the development of atomic clock networks, and also are beginning work in quantum networking and applying time and frequency techniques to that area of quantum technologies.
Okay, beautiful. One thing that I love about our panel, our first panel here today, I found that triangle between industry, government, and then academia to be a really helpful explanation into the landscape of not only quantum information sciences and technology, but I think basically any other emerging technology as well. And we have at least one representative from each point on that triangle here with us to offer a perspective about not only quantum information technology in the public sector, but where we can improve, and maybe perhaps most critically, where we are realistically going to be going. So, kicking it off, I think, with my friend Nick at Oak Ridge. Can we talk about a little bit of the work that your division is doing at Oak Ridge? Some of the publicly funded Department of Energy supervised work that you think is going to probably come to a more tangible fruition in a shorter period of time?
So I'm at Oak Ridge National Lab, and it's the Department of Energy's largest Office of Science laboratory. And so we're really trying to advance the mission of giving the United States the world's leading science capabilities. And so I'm in the computing directorate, where we have the world's most powerful supercomputer. And we're really interested in understanding how we can develop not only next generation computers, but also algorithms that can run at scale on those computers. And so that's one of the reasons why we're looking at so much theory work in the quantum algorithm space, because we want to develop algorithms that can implement science problems or give us answers to science problems that we can't solve on our current, even the giant machines that we have. So that's one big thing. But one of the things that most people don't appreciate is just because you have an algorithm that runs on a quantum computer doesn't necessarily mean it makes sense to run that algorithm. And so we often will talk about things like the complexity and the scaling favorability of algorithms, because what we want to do is we want to understand that we have a quantum algorithm that does something useful and when it does something useful. So we need to understand, well, what are the hardware requirements for the quantum machine that we can start simulating things that are interesting from a science perspective. And so along with those theory things that we do, we also have multiple platforms in quantum computers that we're developing. And you know, it's a constant cycle. So a lot of times in Department of Energy, we talk about co-design. And so that cycle is we push the experiment, we push the algorithms, and then when the experiment comes back, not necessarily agreeing with the simplistic, you always start with the simplest thing first. So when your experiment gives you some data that doesn't necessarily match up with your theory, then you have to do some simulations and update your theory. And so it's a constant cycle to advance science.
And I hear requirement, and I immediately think to NIST. Tara, I know that your agency has done quite a bit in terms of actually standardizing a few of the post-quantum cryptography algorithms, one of those really hot topics in the quantum computing arena. Can you talk about the work that you might be doing in that vein as well, and how some of the research coming out of Oak Ridge National Laboratory might make its way to a NIST standardized operation?
Yeah, thank you for the question. So, you know, honestly, I'm not an expert in post-quantum cryptography. This is an area that NIST is working in. My research area is more focused on things like quantum sensors, but in terms of quantum technologies, the way that it fits in with the NIST mission is that, you know, we have a very strong focus on the development of things like standards, but also on novel measurement tools. And quantum technology shows up in these areas of, you know, enhancing measurement, as well as the idea that we're developing technologies that can help to support quantum technologies, right? As well as industry and other national labs. And so that would be my answer for that. So I apologize that I can't speak to the post-quantum cryptography part myself, but if anybody has any specific questions about it, I can connect people to the right sources afterwards.
No, not at all. That's of course. Perhaps then we can pivot to some of the work that NIST is really focused on actually on the sensor front. I talk to a lot of researchers in that field, and they tell me that quantum sensing has definitely been kicked out of the limelight by quantum computing a little bit. So maybe you can talk about some of the more exciting applications in that field.
Well, I mean, I'd say that in some senses, quantum sensors are kind of one of the better developed of the quantum technologies. I mean, we've had atomic clocks around since the 1960s, so we use those to actually define time. They're used in our GPS systems. Using atoms for magnetometry is also another application that we have at NIST. And in some senses, these have a higher readiness level than things like quantum computing or quantum networking. So I hope to actually be able to see us, utilize these more generally in commercial applications as well as in military applications in the future.
So speaking of commercial applications, that is a great segue to, yeah, you already know, our friends at Microsoft. I'd love to hear a little bit more about what Microsoft is doing on its own proprietary research front, but then I definitely want to talk about the notion of public and private sector collaboration. And that's something that has already been mentioned in the introductory discussion, but the Biden administration in general has placed a very large emphasis on the need for better communication between those two entities in general. So let's start with, what are you doing at Microsoft?
Yeah, definitely. I think we're probably well known in the industry as the only company working on topological qubits, which some physicists and theorists think could be the only technology that will scale the whole way. Um, we have exactly 0 qubits right now today, so there hasn't been a tremendous amount of progress, but we do hope that it's going to be a turtle and kind of hare type of scenario. Given that, we've started to also work with our partners. Microsoft's always been a partner company. We recently worked with Quantinuum and their ion traps to come up with some of the first logical qubits. And, while it was just 4, we think that's a big stepping stone into a new era of computing. I think we've been in the NISQ era for quite a long time. I've talked about logical qubits since 2019, but I'm starting to actually hear it in conferences, which is good. I think we need to progress past just talking about the physical qubits, but getting into logical qubits and what those are and why they matter. As far as like public and private cooperation, we of course believe in that a lot at Microsoft. We've looked at, similar to what Nick was talking about, the different use cases for quantum computing going forward. There's a lot of algorithms out there. We've worked with hedge funds that want to make tons of money. There's optimization, there's scheduling, there's a lot of different use cases. But we've come up with something called a resource estimator, which looks at how many qubits it is actually going to take some of these algorithms to do. And what we found, kind of ranking them, if you will, is that things in finance and optimization are going to take on the order of 10 million qubits, which, given that we're at about 500, is quite a ways out. And I think a lot of people in this room understand that, that we are quite a ways out. But things like computational chemistry and material science, since those are inherently quantum mechanical systems in the way that we want to understand them, we think that we could get to those within 1 million qubits or 100,000, which is a power of 10, and that's a big deal for us. So we've started to concentrate on those particular use cases in computational chemistry, and we've participated with Pacific Northwest National Labs, PNNL, to do some of that work, and came up with a new type of battery that has less lithium in it, which is great for the environment and things of that nature. So we definitely see the public-private type of cooperation. It has to be done. It's going to take a village, an ecosystem to get this done. It's not one company, and Microsoft realizes that.
Speaking of the village and the ecosystem, and definitely a collective approach, I think, Jessica, you are the most qualified panelist, at least, to talk about that. Can you talk about what is going on at George Mason University in terms of really being able to cultivate a workforce ready for a lot of these technological challenges? I mean, that is something that we hear time and time again, is where are we going to pull our workers from exactly?
Sure. I mean, and I think that's a huge problem that we have right now, right? We've developed we took the short route to creating a master's program within our physics department because it didn't require all the approvals and we wanted to get it online fast. We're now going the long route to try to create one that is actually more interdisciplinary and matches our needs. But, universities are slow, right? Getting these programs online, getting students into them takes some time to get them prepared. And one of the things that we're finding in our work is that, that awareness piece is really important too, right? Students are interested, but they don't know what it even entails to get involved in quantum information science. And the other problem that we need to face and tackle is that the universities like Mason that have programs are actually the minority of institutions out there. We need a much broader workforce. We need to be drawing from the population much more broadly. So we've actually started to run some workshops, sort of working with students at other institutions, because if we're going to address the needs that all of you have to get people into this field, it needs to not just come from the handful of research institutions that have large quantum programs. We need to start getting students, especially the undergraduates, interested at all types of institutions, having them take courses, having them understand what quantum is and what path they can take. So we have been developing workshops for sort of early college students to get them involved. And one of the things that we found, actually, that to our surprise, is at the first one, actually, there was a graduate student from Howard University who was at it. We're sort of like, well, okay, we were kind of aiming at community college, maybe some early college students. He was an electrical engineering PhD student and was really interested in learning more about quantum. And despite the fact that they have, right, the BCU Quantum Center at Howard and all of these things going on, this was something he got value out of. He said, you know, he learned a lot. He actually came and took my class this spring after that, and then helped set up an event at Howard after it. And so what we realized, and we also ran one at Bowie State and had graduate students coming to us saying this was really interesting. They learned stuff and were interested in they were computer science graduate students pursuing more about quantum. So it's really across that education spectrum that we need to be engaging students more deeply. And we need to figure out how to get them prepared to take those next steps so that they can actually come enter the workforce. And so we're on the far side of it. I will also say we've been doing some work, as I mentioned earlier, even in K-12, because we think that raising that awareness is also really important to get students excited. We know students start leaving STEM very early on. And so, you know, quantum's interesting and it's an exciting field. I'm actually an astronomer by training, right? We use astronomy all the time to get students just excited about science in general. And I tend to think that quantum's another place we can do that. So it's really going to take sort of this whole pipeline of engaging with students, figuring out how to move them along, and developing the programs. Yes, we need our PhD students, but we need students at all levels starting to engage in all of this work.
So is that what you find to be broadly the most challenging part about educating people in general regarding quantum physics and quantum technology, is simply being able to stick with it?
I think it's finding the path. I will say the other thing is that it does have a reputation for being really hard, right? We interviewed students, and the number of students said, well, you have to be a genius to do this. That's a problem for what we do. We have to help students understand that, yes, it's going to take work. It's hard. It's not an easy subject by any means, but that you don't have to be a genius, that you can do this if you're willing to tackle it. And I think actually that's maybe the biggest barrier and message we have to get out there to people, that this is exciting, it's interesting, and it's something they are capable of doing.
Yeah, I agree. I mean, as a reporter covering this with very limited kind of background in physics, I think that just kind of going back to like a very rudimentary, okay, we're really talking about subatomic particles and subatomic structure. That's helped me as a layperson immensely. And even just this morning, I met a woman who is a chemist by trade, but she actually is working much more into the quantum technology realm. And while, you know, she was explaining that, yeah, you know, there are common denominators in what I've done in both areas, it's definitely, it hasn't been the most intuitive. But, you know, I certainly, I kind of think that having a bit of simply a welcoming demeanor and doing a lot of outreach on every front between government, between education, and between private sector, strengthening that pipeline is a lot of what I hear from different people who are really at the educational forefront. And Tara, now that I can see you on screen, you were nodding along for a minute there. I wanted to offer a moment to comment maybe from the NIST perspective. You guys do offer several internships or fellowships. So, you know, what can you tell me about the government approach to trying to broaden the pipeline for more scientists and researchers in the public sector in general?
Well, I think that this is actually an enormous challenge. So at NIST, you know, our mission doesn't include education or outreach specifically. The way that we help to develop workforce really is through hands-on work opportunities. So we have graduate students work with us, we have undergraduate students work with us, and postdocs, as well as high school interns, right? But one of the big challenges is that if you want to broaden your pipeline, you have to have more people who know that quantum technology exists, that it's something that they can participate in, and to, minimize this idea that you do have to be a genius. This is one of the big, I think one of the big misconceptions, right? Because what people think is that you need to have a PhD in physics to be able to participate in the quantum workforce. But what we see from the workforce perspective is likely half the people that are going to be working in the workforce don't need to be deep experts in quantum, right? We need people who understand how to market, who do product development. We need an enormous number of technicians to help to support this industry. And trying to be able to develop programs from the government side to enable that kind of learning, at the community college level, right, or at the undergraduate level will be really helpful. And one of the big challenges at NIST is, our focus is very much on research. And so we're looking for people to come into our labs and do this research, usually with, who have a focus on, PhD or engineering. So I would love for NIST to find some way to be able to help develop, technicians in the nation to support our industry partners, our industry right here in the United States. But one thing I did want to mention is this idea of demystifying quantum, because that's the focus of this panel. And I'd say one of the big challenges in demystifying quantum is to create more accessibility around it. The reason that quantum is perceived as hard is because it's something that we don't have experience with. The more exposure you have to something, the less weird it is, right? And the problem is that from an education standpoint, there are a lot of high schools that don't even offer physics, right? There are a lot of students who don't take high school physics. And so if you're getting people to have not only interact with the idea of physics, which people perceive as hard because they're only exposed to it maybe in high school, the idea of now interacting with quantum physics seems almost impossible, right? And so if we're able to, discuss the ideas of physics, how cool it is, right? Make physics more interesting experimentally, from the elementary level, from the middle school level, then what we'll do is we'll create more comfort around this idea of physics in general and more comfort around this idea of quantum.
Go ahead. Yeah, get on.
Yeah, I think it's a great topic in terms of what we have to do to get the workforce bigger and the tunnel of quantum bigger. It's something I'm very passionate about. I was a software engineer for 20 years, and in 2019 I got into quantum computation, and I started studying Q#, which is the Microsoft language. And I thought it would be pretty easy, it's just like C++ or C#. This shouldn't be too bad. I'm just learning a new programming language. And I just remember immediately seeing vectors, matrices, and I was like, I kind of remember that from linear algebra. And then tensor products and everything else. I don't even think we learned that in linear algebra. And so, I thought I was a somewhat smart guy as a software engineer, but I was not going to learn this within 3 months or 6 months. I quickly realized that. And so for myself, I went back to community college, even though I'd got an undergraduate degree in physics, but it had been quite a while, and retook linear algebra, calculus, all those different math subjects. And then I wrote a book it's called The Essential Mathematics of Quantum Computing, and I tried to meet people where they're at. I started with just 2D vectors, Euclidean vectors that we kind of all learned, I think, in elementary school and high school, because I think, for better or worse, and no offense to physicists, they dominated the quantum computing and quantum technology, and still do to this day, of how it's developed. So when you see things like quantum computing, a lot of it's because the physicists had no better idea of how to do it, right? So they're like, superposition, that sounds like a great word, right? Entanglement, would love to have that. Interference, nobody really knows what that is, but let's do it, and of course it does mean something to a physicist, and I've learned over time what that is, but different things like, let's have a bra, let's have a ket, let's do Dirac notation. I mean, it's just so many things where the lingo is not even at the level of a student trying to come in that's not a physicist, that I think it's incumbent upon us, and even the physicists, to come up with better ways to talk about quantum technology. I mean, I had to retake Quantum Mechanics 1 again about 3 months ago, and we're still on the Griffiths undergraduate textbook, and basically it's just shut up and calculate, the same deal that they've always done with physics. And I don't think that's helpful personally in terms of learning physics, learning quantum. I understand that that's the way physicists have done it for 50 years, but I don't think it's going to be helpful to open up the workforce much bigger than that.
Well, Nick, I'm dying for your perspective on this as the physicist sitting up here.
Okay, so yes, so I've been thinking about quantum physics for a very long time. But I realize, and I have realized for some time, that that's not the only thing that you need. And so I'll use the organization that I lead currently as an example. So I firmly believe that it's going to require a community to speak the same language and different expertise in order to move things forward. And as a result, I've hired people that are computer scientists, mathematicians, materials scientists, mechanical engineers, electrical engineers, physicists, optics people. We're all working together to try to solve these challenges. And at a national lab, part of my job, so I've got a science job where I'm leading science projects, but I've also got a manager job where I'm trying to develop scientists and help them get to their full potential. So part of my job is to develop those scientists, and they end up going all over the U.S. and get hired into leadership roles in companies. Like we had one person leave to go to Cisco, another one go to AWS, and they're just all over the place. So part of I think what we're trying to do is develop a community across the U.S. that speak more than just physics language in order to solve these problems. And as a physicist, you're basically trained to build an experiment in a very controlled situation to show that something is possible in most cases. Whereas if you sort of get out of that physics mode and you think more about systems engineering and trying to deploy things that have to go out there and work in the real world, it's a very different way of looking at things. And so one of the things we've been trying to do is to try to bridge those gaps between different communities, as well as to bridge this gap between something which is a proof of principle experiment and something that has to work in the real world, where not every knob is easily controlled by the person in the loop.
Well, we're up here. I like the idea that, we should be united by language. I mean, as a writer, I like that a lot. And I don't want to be too pessimistic while we're up here, because as we've already outlined, we have so much promise, so much potential, and a lot in terms of atomic clocks, a lot of opportunities which are already occurring in real time. One challenge, though, I think that I encounter a lot talking to experts in the industry, mainly physicists. They talk about the hype, right? I mean, if we're really here to demystify quantum, then I think we definitely should be speaking in terms of reality. They talk a lot about hype, and they talk a lot about how we, frankly, lack a lot of the hardware and software that, a lot of optimistic where a lot of optimistic projections lie in terms of quantum computing can help solve the climate crisis and maybe provide a lot of more efficient answers and pathways to existing problems, provide advanced data analysis. And the answer is yes, it can in theory, but we're quite a long way from getting there. And this is only what I hear. But I think my panelists generally agree that, in terms of quantum computing, which gets so much traction, that it's still an immature technology. We have a lot of great work happening. We have a thriving private sector ecosystem, but it's still an emerging technology. So on the note of that challenge, and while I have panelists here from academia, from government, from private sector, how do you think it is best to unite that community in terms of coming together and being able to actually overcome some of the very fundamental limitations which are, bottlenecking the industry, as we've discussed today? And maybe I can kick that off. We can start with Tara on that front, definitely from the government perspective.
Yeah, so hype is definitely something we speak about a lot in government, right? In the end, for us, it's not so important to develop products. You know what I mean? We're developing technologies. We're trying to support U.S. industry, and I think one of the big issues around hype is funding, right? So the reason that people hype the work is because they want the funding to be able to pursue the dream of quantum computing, right? And so, in some senses, if you want to reduce hype, there has to be some continuity in funding to ensure that these companies are able to continue with the work that they're doing. That would help, I think, bring people down in terms of how they speak about their technologies and where we're at in their applications, right? In terms of, trying to bring us to the next stage, right? So quantum computing is still very much in its, I'm trying to find a good word. I came up with this negative word in my mind, but it's still to some extent a research product. You know what I mean? There's a lot of promise in it. The question is I'd say from the government side, what I see is that we have a tendency to try to use physicists as engineers, which I don't think is the greatest approach, right? I don't think that the government itself uses its workforce as efficiently as it could. If we really wanted to do things like create really, really high performance, portable atomic clocks, it would be helpful not to have graduate students design these systems. It would be best to be able to take the engineering perspective and unite that with physicists to be able to figure out, how can we collaborate in ways that can actually really advance the technology aspects of things. Some of the big challenges that we see at NIST are even just simple things like the availability of different types of laser sources, right? That really does limit the types of atoms that you're working with. We don't have things available like we do for electricity, right? We have microelectronics that are available for electricity that allows us to make things small. We don't have so much of that from the optics side. So what we really need is we need a big push in terms of making photonic type chips, right? So you can make things like ion-based quantum computers smaller and more robust. And so, if government were able to partner more with academia, partner more with industry, right? So that we can understand the greater needs of all of these industries and collaborate more efficiently with one another. I think that with some engineering, we would be able to more efficiently advance some of the technologies needed to actually bring, these quantum technologies to fruition.
Definitely. Nick, your eyebrows jumped when she talked about efficiently utilizing the current federal workforce and physicists in particular. Do you have a comment on that?
Well, I guess the thing that people need to realize is that there's a fine line between advancing the science and then explaining why we're advancing the science. So, the reasons that we're doing these things are based in science, but where we're at in terms of moving and advancing the technology and our understanding to get to that bigger goal, I mean, there's a big gap there. And so the only way that we're really going to close that gap and develop the technologies that end up being, in your phones that you're carrying around with you potentially is to work together with these interdisciplinary teams of scientists and engineers. And there's really a lot to be said for work experience. I mean, a degree is great, but the work experience that you get developing these things is really where the rubber meets the road.
Mm-hmm. Well, on work experience, Jessica, would you like to comment on that as well? I mean, I hate the notion that, it shouldn't come down to maybe work experience versus academic qualifications. I don't think one is maybe inherently better than the other, but certainly they both have a merit and they definitely have a place in this emerging field.
Yeah, no, I think that hands-on experience and the work experience are really important parts of all of this. And I'll say, I mean, it's something we've built into the programs we've been creating, is that's actually the internship part of it is a required part, because we know there, especially in an emerging field like this, there's only so much you can understand about what's happening, especially in industry. If we're really preparing students for industry and those kinds of opportunities, they need to see what they are for themselves. So that is actually part of the design of the program. I also want to just comment on this sort of issue of where we are in terms of hype and understanding, what's coming. and even the uncertainty, right, in what's coming in terms of these technologies. And I will say that students are aware of that. We've asked them about, whether they see quantum as a risky field to pursue, and they say yes. Some of them are excited about that and say it's still worth it, and they're, things that they can do. And those are often our PhD students, whereas the undergraduates are like, I'm not so sure. I'm not sure what that means for a job out there for me. So I think that is a factor that we're trying to manage and figure out, and sort of they're seeing those opportunities and getting their hands on them and getting to see what industry is doing is actually maybe an important part of breaking through that feeling that there's a risk and getting into something that you don't know where it's going.
I mean, our introductory speaker, he was saying that he definitely chose his PhD correctly. So I don't know about too much uncertainty in terms of employment. But on maybe more of an employment front, Microsoft is a huge company, a huge tech company. And there we have researchers, we have people working within benchmarking and standardizing quantum technology, we have workforce development. But what else is Microsoft as a private sector company really working on in terms of contributing to the quantum information science field? And where might some of these, potential job seekers with whatever qualifications they bring to the table find themselves at Microsoft?
Yeah, I think that's a very important question, and I think some people have already talked about it already. In that, we hire marketers. We need really good marketers. We need people that are in sales. We just hired a huge sales team. I used to not be a big fan of sales, but my wife is in real estate now, so I have to be a big fan of sales. But they need to understand quantum at a certain level too, and it's incumbent upon me to help educate them about it. Obviously, I'm not going to create a quantum physicist overnight, but they need to know enough to be able to talk to customers. Our marketers need to know enough to do messaging. Our legal department I work with, they need to understand, in terms of intellectual property policy with different world governments. We cooperate with people on the Hill, things of that nature. We hosted a dinner with different people from the government and public sector. And what struck me was just how little they knew about quantum. And to be quite frank, AI was dominating the conversation.
Yeah.
They were like, quantum's great, but what's up with AI? And so I think that's another thing that we have to deal with is, to keep the conversation going. And then, everybody's like, well, quantum's going to save AI and all this other stuff. And I don't know about all that. But there are multiple avenues for people to get involved in quantum. Microsoft's a huge employer. And we look to do that. We also need leadership that understands that have gotten their MBAs, but also can direct quantum physicists where to go, right? So they have to manage people that they don't know what they're talking about. And so that's not an easy thing to do. So there are a lot of different job opportunities. And the biggest question I get when I'm talking to customers is, when is this going to be real? Like, when are we actually going to have a quantum computer that works and everything? And my favorite answer so far is it's a probability distribution from 1 year from now to infinity. And infinity means it never happens. It's just really hard to tell. We could have the ChatGPT moment. We may not. I do think that when I talk to companies, it's going to be a moonshot type of effort to, the amount of effort that the United States had to put in to put a person on the moon, in a more negative light, the Manhattan Project. It's that type of technology leap that we would have to make, and there has to be the political will, the companies, everything that went into that, the engineers, the people that came up with the masking tape for the people on Apollo 13. I mean, it's that type of technology that we need the cooperation around.
I'm glad you talked about that probability distribution. I think if there is one thing that maybe people watching or people here might be able to take away, it's, grounding our discussions in reality and really where we are from theory and research and development and practice to actual deployment, and then way, way, way down the line, commercialization, right? And I hate to be too negative. I don't want to harp on it too much, but I think all of you guys are all friendly. You're all nice, right? So between academia, government, private sector, I mean, what are some of the hindrances? And we have looked at them with the introductory discussion, but maybe in your individual experiences, what could be improved to help a lot of the collaboration, to help all of the boats rise, as the introductory speaker put it? And maybe we can start with Jessica on that front. You're definitely at the kind of ground floor of it all in terms of a workforce development.
Sure. I mean, I guess there are two aspects of this, and I won't speak for my more technical colleagues who I know collaborate a lot with both government and industry, and I don't, know the details of where those bottlenecks are. I'll say for us, it's really identifying those opportunities for students to get involved, and also I would say for us to understand what it is that industry needs from that workforce, needs them to know, needs them to understand. I mean, we've been actually doing a lot of interviews with industry to try to actually get at that as we build our master's program and make sure it's well aligned with that kind of work. I mean, I think for PhDs, we have a pretty good model, right? We know that they get involved deeply sort of in the technical work. They sometimes collaborate with people in industry. But I think as we're moving to understand how do we prepare more students, especially at something like a master's level, that integration is really important. So that communication piece is really important. So Yakov, I think hit it right on the nail on the head with the idea that we do need that communication. We need to know what's working, what isn't, what they're seeing as the gaps as these students are coming out and moving into the workforce.
Okay, nice. What do you just monologued for a minute here about that in particular? And I mean, talking about having people who have some type of awareness about quantum physics technologies in general at any level within Microsoft or another comparable large company or even small to medium sized business looking to get into the industry as well. Is it really at the end of the day for you guys either having PhD, very technically minded researchers and physicists, and or people who just know, hey, I'm not trying to sell a car without an engine. I need to know how this works. Is that kind of the duality that big tech companies are looking at?
Well, I think, one specific problem that I deal with on my day-to-day job at Microsoft is having a field team in a company that only, I don't want to say only cares about AI, but it loves AI right now and open AI. And we just don't have the funding right now to have a field team. And so we have tons of people that are Azure Cloud Solution Architects or software engineers that have a passion for quantum computing and want to get in front of companies and talk to them about quantum and our technologies and our platforms. And we have about 100 of what we call quantum ambassadors at Microsoft, and they do it in their volunteer time. And so they're globally distributed, and they get experience. They get workforce experience by doing these engagements with other companies and how quantum technologies work. And they have a real passion. I think, harnessing that passion, where to put it, are big things at Microsoft. And in general, I think, the original question was kind of like, what is the biggest problem? What's the biggest challenge right now, I think, in quantum? And it's the word itself, I think, in a lot of ways. I drive past Quantum Park or whatever, right? And like that has nothing to do with quantum, but it just sounds cool. Comcast will have like the quantum internet, and I don't think it really has anything to do with quantum. It just sounds fast. I mentioned something, quantum to my wife. She's like, you mean the Quantum Leap TV show, So just getting past the quantum and saying, hey, this is something that we can talk about. We've gotten to a point where computation is something that we can talk about and nobody freaks out. We have to demystify this quantum word. And we have to bring it down to a level that everyone can kind of agree where we're at. My elevator pitch is that we do computation at the level of electrons. And people are okay with that. They don't get too freaked out. So yeah, I think that's the biggest challenge right now is not the computing word or the sensor word or networking word. It's the quantum word. That very first word usually turns people off, or they're just like, well, that's straight over my head. I don't want to talk about it. So yeah, that's kind of my thoughts.
Okay. All right, to my government speakers, in terms of bringing a little bit more interplay between academia, private sector, and then you guys respectfully at NIST and Oak Ridge, maybe Tara, you can talk a little bit about what can be improved in terms of having more discussions like this, right? And having more collaborative efforts toward quantum information technology development.
Well, one thing that I see as a challenge in government is that, or, at least at NIST, is that, the quantum community isn't very well united. They're not united in terms of the language that they use. They're not necessarily well united in terms of the technologies that they use, right? We worked in very siloed ways. What I see from the academic perspective is that there's not an enormous focus on collaboration, right? We have, as the United States, a focus on superstars, Nobel Prize winners, right? And quantum inherently will require leveraging the talents of many people, right, from many different types of backgrounds. And this is something that I don't feel like we have an enormous amount of experience with, and it's not a focus that we have from the academic perspective of physics. So, and another challenge that I see is, physicists or researchers don't have a lot of education around science communication, right? This is going to be challenging within industry, within academia, within government, right? If people cannot describe their research to people in a way that they can understand it at different levels, at different education levels, then we're going to have a big information blockage, right? And so I feel like this is an important part of the education process for physicists, is how do you actually communicate physics without jargon, right? So this is the big challenge around quantum. It's the jargon, and the fact that the jargon is not the same across different quantum technologies. And also, one of the big challenges that were mentioned before was this idea of, where are we drawing our workforce from? So, at NIST, we have opportunities for people to work in our labs, right? So we have, 3 different campuses. The main ones that do quantum work in quantum are in Boulder, Colorado, and Gaithersburg, Maryland, right? And, these are generally well-to-do communities, right? That, you're drawing on students from local universities. And so, how do we broaden geographically the opportunities for people to engage with quantum, in national labs, in academia, right? So we see the strong focus of work opportunities that are available at R1 institutions and well-funded labs. And, those are generally located on the coasts, right? The universities associated with those are generally accessible to, top students or students from high economic classes. And so, if we really want to broaden our workforce, we need to draw on the full capacity of the United States population. And I feel like we're not doing very well at that. We don't know how to solve these problems. What we need is very clear direction in terms of growing this pipeline, in terms of collaboration, in terms of education and communication around things, so that we really can facilitate these collaborations between university, academia, and industry. And finally, the thing that I'd like to say is that we don't have a good feedback system, right? So this idea of industry, government, academic partnership sounds wonderful, right? But we don't have a lot of feedback from, let's say, industry to academics, and, do we want, industry to be driving academic research? Not necessarily, but sometimes people are, sometimes, researchers can go off into kind of wacky domains to be able to like refocus them a little bit, right? To have some concerted effort in terms of ensuring that some of the research is actually helping to support industry would be helpful. So, how can we facilitate these conversations between industry partners and academics and government would be really helpful. And we have some opportunities, but I don't think that they have a very well designed direction or communicated direction. And so, yeah, the how. It would be great to know the how for all of these things. And that's where I see there's some big missing elements.
That's a lot. As a leader within one of the well-funded labs, which does not have a coast, Mike, you want to give us some thoughts on this as well in terms of enhancing collaborations between your peers in academia and private sector, and perhaps All of you have talked about jargon. I didn't realize it was such a large issue within the quantum information and technology community. But, what are your thoughts about maybe having more productive and collaborative discussions, which can lead to some great breakthroughs or improved outreach?
I mean, it is very, very true that quantum information science is very diverse from an approach perspective. So there's a lot of people working in fundamental materials research, and sometimes that's leveraged to move a particular technology along. And so we're going to require these kinds of diverse collaborations between experts. But in terms of the feedback loop, physicists are maybe not the best example to look at to try to develop a totally new workforce and capability, because you go to your undergraduate for 4 years, you spend 6 years in graduate school, you might spend another 6 years as a temporary postdoc type employee. Then you've got 5 years to make your name typically in the first part of your career. So the feedback loop is a really long one to say, oh, now I'm an expert and people recognize me as an expert. I think we need to figure out ways to have feedback loops, in particular with internships. So Oak Ridge National Lab, we have more than 6,000 people who go to work there every day. And we have this summer, I think the number I heard was 800 interns who are going to come to the laboratory and have an experience with scientists and engineers. And I think that's really valuable, because the things that you learn in school, I mean, some things are very valuable, like learning how to write. Science communication, I went to liberal arts school. That was the most important skill I learned in college, was how to write. And I'm a much better writer than I am a speaker, so apologize for that. But the thing that we need to do in these internships is get people talking to scientists, talking to engineers, figuring out how to solve problems. What are the things that you do in your job that make you successful? And you can go back and say, oh, well, I guess we talked about that maybe in one of my classes. Now it's interesting to see how it's actually applied to do something useful.
Well, you're a very good speaker, so I don't know what you're talking about, but I do know that we've been a little, we've been doing a lot of reality checking here. We've been not negative, but realistic. So maybe with the approximate 10 minutes we have left, everyone can kind of go down and talk about their favorite thing within quantum technology, or something within the field that is very exciting to them. Something that you're curious about, or that you feel like other people should know about, should get more attention. And I know it's kind of a bigger question, so I'll let y'all volunteer. Who wants to go first? Oh my God, I have to pick. Yeah.
I'll go first. Sure.
Yeah.
So, so I'm an experimentalist. So I look at things in terms of what I can actually do in the lab and see. And so for me, I have to be able to do it for it to be real. But at the same time, I said earlier that we're always looking at this from the perspective of what capability does it enable. And so you could look at these quantum devices, whatever your quantum device is, and you could look at it as a sensor and a computer, and something that, when we talk about scalability, as a network. And so what it really excites me is the idea that I could build these quantum systems up into an infrastructure where now I can do computing and sensing, and I could build, in particular from the DOE perspective, science capabilities that don't exist. And so I'm going to be able to make measurements that I couldn't make before. I'm going to be able to discover new science. I'm going to be able to compute things that I couldn't compute before, and discover new ways to do things that people would love to have, but we don't know how to do. So for example, battery technology. If I had a battery that was so good I could buy my cell phone and never have to recharge it, I think everybody would like that, right? And so these are the types of things that I think quantum technology could enable.
I'll sort of take two different routes here. The first is, the sensing work that's being done is something that always really, really excites me. As an astronomer by training, being able to understand our world in new and different ways, and much more sensitively than before, is amazing. I mean, LIGO, of course, is one of the big examples of all of that. And I was working actually in the director's office at the National Science Foundation when that discovery was made with an astronomer as the director. And that was a really exciting moment. So, you know, we're going to learn lots of things about our universe with these kinds of detector systems, which I find amazing. But for me also as an educator, the excitement that students get about science and to see this kind of work, the number of students who've said, wow, I'm really interested in this stuff now, when we've run programs and shown them some of the things that can be done, and you know, talk about that it's increasing their interest in science in general and quantum specifically, is really exciting to see. And where that takes us and takes all of them is something I look forward to seeing more of as we go along.
All right. What do you want to jump in?
Yeah, it's hard to pick a favorite topic,
Yeah.
but I think recently, you know, I'm always trying to learn more about quantum and quantum computing. That's one of the cool things about the field, is there's so much to learn. You're never going to run out in terms of things to try to learn. But the advent of ChatGPT has been really cool for me. There's been lots of times where I'm reading a quantum book and I'm like, I have no idea what that means. And now I can type it into ChatGPT, and hopefully 99% of the time it gives me a right answer and doesn't totally hallucinate. But that has been really cool for me, to have access to basically a professor that can help me learn quantum technology, some of the newer things where I could put things in a Dirac notation and have a math problem and I'm not really sure how to approach it, take a picture of it, send it to ChatGPT and say, you know, do this, this, and this. That has made me very excited, because it's another avenue for people to learn, and you don't have to have access to a physicist or whatever to answer some of the questions. So I think that technology, it's going to impact a lot of places, but I think in quantum, it's also going to help out a lot as well.
Yeah, you get to teach an algorithm about quantum theory too. Anyone can learn it. That's amazing. Tara, do you want to bring us home? What's your favorite thing that you get to work with in terms of quantum theory and technology right now?
But I'd say that, you know, from the NIST side, we're very interested in the measurement aspect of it and the sensing aspect of it. You know, where will this lead us, you know, in terms of technological capabilities, if we can improve measurement? You know, personally, what I'm really interested in seeing is, you know, assuming that quantum technology does take off, what I'm really curious about is how the public is going to take it and then repurpose it, right? So when you think about something like the laser, people weren't thinking that the laser was going to be used for, you know, medicine, right? For entertaining our cats, right? And in the end, it will be really interesting to see where the public takes quantum technology, you know, when it is finally realized. And the third thing that I'm really excited about is this idea, right? This is a vision or a hope for the future that the United States will see the benefit of quantum education, right? And kind of the inspiration that I hope students and the public will get around the opportunities in quantum and kind of the beauty and inspiration that there is around physics. So that's what interests me.
Okay. Well, I don't know if we've demystified quantum exactly. We've talked about a lot of new topics. I've learned a lot. That's one of the reasons I really like to do these moderating panels, is you guys individually teach me a lot. But I think one thing that we can really take away is that there shouldn't be a lot of fear or hesitation surrounding getting to know a topic which is foreign to many people, which doesn't feel intuitive, but at the end of the day is wildly impactful to everyone, right? I mean, it's physics. So we've talked a lot about jargon, we've talked a lot about collaboration, and I think that everyone should kind of walk away from this feeling a little bit more confident that they do have a place in the quantum information and science industry, wherever it is between academia and private sector. Down to the 1 minute mark. Okay, we have maybe time for like one audience question if we're kind of thinking about it. What do we think? Yeah? Never mind.
Here you go, just your name and affiliation.
Art Nysick, DAU. the one thing we hear, or the fear of quantum, is it's going to break encryption, and we all have to prepare for that as compared to supercomputers. Is that something I mean, are nefarious uses being, out there, and who's doing that, or is that something that is real, or is that something that is we should be concerned about, or what's your opinion on that issue?
Take it away.
So that's probably the second most asked question in my customer engagements. Uh, there's a lot of hype around Shor's algorithm, the one that can factor large numbers. But I do think there's the whole harvest now, decrypt later type of thing going on among our adversaries, where they take encrypted messages that they can't break right now, but in the hopes in 10 years when that possibly is done, they could decrypt it later. And even nuclear secrets that are 10 years old are still very sensitive. So I think it is something to think about now. I think that's why the administration put out an executive order about, starting to do post-quantum crypto, and NIST is starting to act on this. It's a very important question. The fact of when that quantum algorithm is realized, I think, is at least 5 to 10 years out, but there is the thing of harvest now, decrypt later.
Can I follow up with that? Is that where we should be doing zero trust principles? How do we prepare? Because when I talk to federal agencies, they have no idea. How do I prepare for quantum, like quantum resistance? Do you have any?
Yeah, I think, having worked in the government, it's not always the most agile organization, but I think we have to get better at being able to change out security protocols. There's no way to really prove, even the post-quantum cryptography ones, that they're going to actually be impervious to quantum computing. So if we select one and we find out that that's not the right one and we have to change it out again, I think that organizations need to become agile about changing their security protocols throughout the organization and not just have SSL and TLS.
One more.
Mark Kagan, Panoptis Intelligence. Talking about the problems with getting young people engaged in STEM and all this. Just one suggestion. Instead of being worried about it's hard and all these obstacles, my observation over the years is one way to get them engaged is talk about how cool it is. And I noticed that Leonard used the word cool 3 times when he was talking. And if you talk about how cool it is and push aside about, that it's hard, that you have to work hard, that you have to talk about the 4 years of undergraduate, 6 years of graduate, 6 years of postdoc and all that, up front, you're going to really scare them off. But if you talk about cool, just the way when I was watching the original Star Trek and saw the technology that they were doing back then, and that inspired so many people to then go ahead and build the CAT scans, the MRIs, the communicators, the laptops, and everything else. And they didn't think about how hard it was and that they'd have to take all those years of engineering and science and technology and everything to do it. Focus on, use the word cool a lot, or I hear the word sick. That's really sick nowadays. Use those words, and Leonard, keep using the word cool. And by the way, my 4-year-old granddaughter is going to build her first quantum computer by the time she's 4. So if you want her resume with bluey decals, I can provide them to you.
All right. Well, yeah. What a sick panel then. That was really great. Really, please give it up for my 4 really incredible panelists. They were wonderful.
Thank you, Alexandria. We're going to take a little break, a few minutes. I still think there's bacon and eggs back there if you need your second breakfast.
When I heard you use the word cool the first time, I was thinking about that right at that second and said, this is karma, okay? And I give you another example. I say this whenever I get the chance when I go to events, all right? I always tell this to people who are nerds in our industry, whatever. And I say, how do you engage? How do you talk? How do you get out of yourself? How do you talk about Star Trek? Because they're trying to
Perfect. Hey folks, welcome back. My name's John Curran. I'm the news editor with Merit Talk. So happy to be back here at an ATARC event moderating. They're really some of the best ever. So we're going to talk today with our very nice panel about Q-Day, and specifically post-quantum cryptography. We're going to run through just a little bit of a level set about the existing policy stuff that's going on, but then really dig into the conversation. So I'm going to start us with some introductions. First, we have Bill Newhouse, cybersecurity engineer, leading the migration to post-quantum cryptography, National Cybersecurity Center Excellence, National Institute of Standards and Technology. Further down the row, we have Ross Ford, senior engineer and ICAM subject matter expert, Cybersecurity Infrastructure Security Agency within DHS. Next down, we have Dr. Charlotte Hinkle, senior physical scientist, science technology assessment and analytics at the Government Accountability Office, which is every good journalist's favorite government agency. Further down, we have Dr. Daniel Corbin, Deputy CIO, Technical Director, U.S. Marine Corps. And last but absolutely not least, Rudolph Rojas, Information Technology Manager at USDA. So just to level set a tiny bit, maybe as much for me as for you, let's talk just a tiny bit about the existing policy around quantum, post-quantum cryptography. You can mark a lot of the sort of policy landscape that's evolving now back to November 2022, when OMB issued M2302, memo on migrating to post-quantum cryptography. Some major points in that were essentially federal agencies needed to inventory systems for their PQC vulnerability by May 2023. Since then, in some of the news reporting we've done, the National Cyber Director's Office tries to shorthand it to a few different issues. The first is for agencies to do your inventory. The second is to prioritize the most important systems. And third is to plan for the transition to PQC. Sounds very easy, not very easy. On the regulatory front, let's quickly cover two things. First, NIST enters the fray. And it's up to NIST to issue guidance on PQC standards. NIST issued a draft last year. We've heard some talk that it goes final this year. And then based on what NIST issues, then maybe down the road, OMB issues more. So intro, Bill Newhouse, can you help us understand the NIST action a bit better?
I hope so. Thanks for the opportunity to help build this collaboration of moving towards quantum readiness, quantum safety, and the conversation is about post-quantum cryptographic algorithms, and beginning way back in 2006, based on a notion from an algorithm that Daniel Shor figured out that, hey, a quantum computer is going to be able to break the math that we use to provide the protections to today's asymmetric or public key encryption. So in 2006, conversations started happening essentially on an annual basis between cryptographers to say, well, we're going to need to modernize and come up with some new stuff. And by 2016, NIST was compelled and asked and offered to lead a process to standardize new algorithms. And it was called a competition to begin with, but the idea and the competition part is put the algorithms in front of people, talk about them, get them submitted into a process that has some rigor so that everybody knows what the standards that they need to meet to be accepted into the process were, and then to iterate on those in annual conferences since 2016 to select the ones that continue moving forward, that haven't been identified as having a problem. And so that was 2016 when NIST took on this process, and last year in late August they put out the FIPS for 3 of the 4 that have made it through thus far. And this started with 80 different submissions, and these submissions came from cryptographic collaborators all over the world. These aren't US standards, these are international standards, and these are, many of your companies have either had the physicists and the cryptographers and the mathematicians already on teams, or you bought them to bring them into your teams later, so you could say you helped develop these crypto standards. But NIST has been running this process, and those 3 that became a FIPS draft are gonna become FIPS final this summer. And you say when, and I will say that I've heard the people who are leading that process at NIST say most likely July. So late July, early July, I can't tell you that. But that means you'll have 3 new FIPS, Federal Information Processing Standards, available to you if you're in an industry where now you've got to offer to the US government the use of validated crypto modules. You can start entering into that process because you have 3 new ones that could be validated through both our algorithm validation process and our module validation process for technologies. Is that enough? Too much?
I think that's perfect. Second regulatory level set.
Well, you said regulatory. NIST is non-regulatory, so there's a lot of other people who get to do this next part.
Ross Ford, you get the call next. We know CISA is working on a PQC initiative, has talked about quantum readiness roadmaps. Obviously, CISA has a lot to do with federal agencies, but much bigger than that, has a lot to do with critical infrastructure that's not part of the government. So root us in where CISA is now.
Well, I appreciate you having me here. And, CISA does have a broad area that it covers. And primarily, we're focused right now on helping the federal government because we can be more explicit in the things we can ask the federal government agencies to do. And then we expect that to be then adopted by other parts of the critical infrastructure, right? Because they'll see ways to do this. So CISA's understood that this is not a quick thing to do, right? Just like NIST has taken a long time to, relatively long time in government terms to develop these new cryptographic functions and to make sure they're standardized, and they will be soon. CISA's seen this happen before. The best example I use over and over is the move from what we called SHA-1 to SHA-2, where we had a need to change our algorithms, and that took quite some time to make that change, right? So we're still trying to help agencies understand to prepare and then make the change. So how are we helping agencies prepare? So you mentioned M2302, that is pretty explicit in what we're trying to do. CISA's creating a document now which is going through approvals. It should be out sometime in the summer, I would imagine, to help agencies understand, particularly how they should make this move to post-quantum cryptography, with the most important aspect right now, right? This is a long-term transition, right? So right now, the things that CISA is going to be helping agencies, really focus on is doing discovery. Sorry about that. To doing discovery and inventory. So it's really important to discover where the cryptographic algorithms, where these functions are in use today in your agency, and then how to then make an inventory of all those things it's protecting. Because knowing the inventory of what those functions are protecting is really important, because in M2302 they said you need to look at your categories of information that you need to move toward protecting first, right? And those things are like FIPS categorization high, HVAs, high value assets that your agency already has categorized a system as a high value asset. And then other pieces of data that may be mission critical data for your organization, but and what is mission critical? It means it, in this case, and it would be relevant to an adversary in like the 2035 timeframe. On the last panel, they talked about, collect now and decrypt later, right? That's the kind of thing that we want agencies to think about. And each agency themselves is going to understand which one of those data elements are important for that. So I think that's kind of what we can expect to see. Probably some timelines are related around reporting, and manual reporting is going on right now, and we want to help agencies do a little bit better with doing automated reporting.
So plenty to chew on this summer. coming out, we think.
I expect so.
Right, okay, very good. So with that level set, which helps me a whole lot, let's talk about sort of the next thing is, we're going to talk about challenges, but first let's talk about maybe things that are going kind of well since then. And from the agency perspective, calling on Dan Corbin first. So, nobody's going to tell any secrets here, right? Everybody's, kind of, there's a little veil, I think, of secrecy and confidentiality about telling anybody about how quantum ready your systems are. So we would never do that. But within that sort of constraint, any thoughts on how this effort's going? It's almost 2 years old, and would love to hear your thoughts.
I'll first start by saying, my job in the Marine Corps is I'll start by saying first, give you some context of what my job in the Marine Corps is. As the, I'm actually the Chief Technology Advisor, is the official definition, and what I generally do in that is look and determine where there's gaps in our current ability to meet the strategy of the Marine Corps, identify where those are. That generally resides in that 5-year period that's often called the fit across the fit up, and identify sort of the risks associated with the adoption of those technologies that are now coming through the acquisition process that another organization or other organizations will provide to them. This falls right in the middle of that space, primarily because it's very difficult. It's a challenge. It's a promise that's always coming. And we don't exactly know when it's going to be here, but we know that it will eventually be here, probably sooner than our current timelines support in a real way. But then you go to the good things that's going on. We in the Department of Defense, and the Marine Corps specifically, sort of take our guidance from the Department of Defense, who helps us prioritize what it is that we're doing, and that generally comes against some mission that they are planning for, and those are usually defined in the national security strategy that we align to and are, I'll say, judged against in our budgets. There's a increasing level of authority that's being executed by the leadership of the Department of Defense over the last 5 years, where they provide guidance to us, and then they have the opportunity to not certify our budget if we are not prioritizing the way we are spending the money across the fit up, like the way they should be. So that really motivates us to align with the priorities of the larger organization, which is the federal government. So what is going well is, we've been working with this crypto problem now for some period of time. Not only that associated with the coming Q day, but there's also just the fact that we have cryptographic algorithms that are no longer secure as they need to be. And so that provides us sort of a timeline on what does it take to actually modify our systems if you have to have a new way to put cryptology on top of it. And those are long processes. In Marine Corps, fairly easy. And we've been making fairly good progress in understanding what we have. So we're really good in that regard. And in many cases, in modernizing the cryptology in our radios is also was rather straightforward for us, which led to a problem. We find ourselves now ahead of everybody else and determine, okay, now we have to slow down because we got to wait for our partners, which is in the national security strategy, partners, allies, and joint forces to be able to support that, right? So everybody has to go together, right? when you come to this stuff, and so that we meet monthly at the DoD level to say where are we in along these patterns. So I think the DoD is probably fairly well prepared to understand what their inventory looks like, at least for the mission critical systems. And when I say mission critical systems, it's for a specific set of events that many of you probably are aware of that in the next 10 years. You pick the timeline in certain areas of the world that we have to support. So that's our timeline. That helps us prioritize everything from the critical infrastructure that supports it to the to the specific weapon systems that we need to do the mission that to safeguard the national interest of the United States. And to your point, it's, yes, there is no secret, but apparently even if it is, they'll be able to break it here in a few years.
Wow, well, being ahead of the curve is the best problem, best kind of problem you want to have. Charlotte, your view on kind of in the past couple of years, what seems to be going well in the kind of early days of that PQC process?
Thanks. Yeah, I'm Charlotte Hinkle. I'm with the Government Accountability Office. We're more in the business of providing Congress with fact-based, nonpartisan information. So it's wonderful that we're having these conversations, but there's always room for more. Long-term sustained efforts are going to be very important for this transition and very important to make sure that we can successfully make the transition. Because if the efforts lapse for some reason, there's not a lot of talent out there. As we heard from our workforce panels, there's a need for more talent in the area. So talent's going to go elsewhere if the efforts lapse. And along those lines, for the workforce, we're very much still developing the workforce. So are there opportunities there to consider? We have people that are smart people that do things, but can we go through and can we train those people to work in this space too, so that we can better use the resources that we have? And there's always, and GAO big on collaboration, right? There can always be more collaboration, and there can always be more stuff that can be done with that collaboration, which can lead to breakthroughs. But there might be institutional boundaries, as we've heard about, to really having that collaboration and to making sure we collaborate well.
Thanks for that. Rudolph, as a tech practitioner over at USDA, I imagine you're involved to some degree in the sort of PQC transition. What's your view on things that are going well in that process now?
Well, I will say that USDA in general has a very highly developed data strategy plan, a forward-looking cybersecurity posture and development of a plan for that as well. Cutting-edge people at the top there under Gary Washington. And so what's going well is we have, for example, we just implemented our USDA data strategy plan in December for the next 5 years, and in conjunction with that, they're working to develop more of a posture for the cybersecurity and the quantum cryptography zero day, I guess you'd say. So yeah, from my standpoint, though, I'm more or less in the weeds there with technology center, the technology center out in Kansas City that hosts a lot of our infrastructure. So I'm working on a daily basis trying to get certificates updated, the latest PKI figures in and keys and all that. And so, I'm really down in the trenches and seeing what's going on. And I'm actually a little concerned about it. I know we have some very good partners, Entrust and Akamai and some of the others, big players, AWS and so forth, who we're also doing some pilots with. So, I know that they're doing their part to stay on top of the NIST requirements, but I'm just hoping that, we don't wait till 2035 to get all this done. So I'm confident it's going to happen. I know we got some great people, but another issue that we have is, as Dr. Hinkle mentioned, is personnel, right? So we have people retiring out. It's an aging workforce at USDA, 100,000 employees. Quite a few of those are aging out. So we're struggling to bring in a really good crop of people that have the technology background that we need. And problem is that they can find more lucrative employment in the private in the private sector. So we got some strategies, but we also have some problems there as well. So.
Right. Interesting rundown. So just something that that I think is an easy word to say, prioritize, but very difficult in the conversation that we're having, to actually look at all your systems and prioritize them. I guess the question is, there is a lot of work to do. And so any advice, and I guess, Bill, maybe we'll start off with you on this one. How should government agencies go about actually prioritizing the transition? One thought is there are varying levels of urgency across sectors, across agencies. So, you know, priorities mean you do the most important thing first, but is there anything, any kind of advice you can offer on how to put that together?
Yeah, so the title that shows my work here on the slide that you can see on the big screen says Leading the Migration to Post-Quantum Cryptography. The word that was left out there was project. And I work at a center where we're trying to do things to demonstrate things that are important to be done. And in this one, we started in 2021 and we invited collaborators to join us so that we could initiate opportunities to share what a group of people think you need to do. And inventory and discovery is an obvious one. If you're going to have to put in new algorithms, where are you going to put them? Where do you rely on algorithms that are deemed vulnerable now is not something that every organization can answer quickly. So we've got 37 collaborators now. We started with 14 in 2022, and we have 37, and we're going to have more. And I'm sure a few more of you will come up and ask me, how do I become a collaborator later? Because I have an inventory tool. Or I want to see how these algorithms work inside the communication protocols that are part of the international standards that we use every day for asymmetric encryption, for authentication, and for digital signatures. Those are true things that our collaborators come together and they were like, we have the ones who want to play with what are the measurements of memory and time to use the algorithms in communication protocols. And then we have the other folks who you know, Sandbox is here, I know, Lee from Verizon's here. Those are two collaborators. And if you're another collaborator and I don't see you, it's because we're always on Zoom for these calls. But every week we're getting together to talk about what we can do. And we put out a publication that said, here's the concept of doing inventory. Here are the places you need to look. And then we put out another paper on here are the first measurements of interoperability and performance against the draft standards. Well, what can happen this summer? We can make those final against the final standards. Inventory. Well, we haven't really run a lot of inventories because you got to have data to do that. And our lab isn't so big that we have a giant network to stare at. But guess what? We built a zero trust architecture at the center as a part of another project. Maybe we can look at the asymmetric encryption in there. We've got to ask all the other collaborators that. But the model here is we brought 37 folks, and that triple double, you know, that's 37 times plus 5 at each organization of expertise of people who are trying to help everybody do something we've never done at this scale before, to look all over your refrigerator to find out where your moldy cheese is, where your good vegetables are, and what you should be eating in leftovers first. That prioritization is a high value asset question. That question's been asked since the first VA laptop was lost 14, 20 years ago. What are your high value assets and how are you protecting them? Those are your prioritization answers that you also can get from your zero trust team, that you could also get from your team that's doing privacy regulations with your international partners and with the states that require privacy laws that are pushing on you. So it's a community. We need to keep talking, and we don't have all the answers yet. Doing an inventory at this scale has not been done, and it's going to give you a lot of, oh my God, I didn't realize I had that closet, not only what's in the closet.
And so really but that skeleton of figuring out what priorities are is being built, is existing. Yeah. Ross, thoughts on that from the CIS perspective, which I know is a little bit different than this perspective, but priorities, how to go about it.
You know, I mean, I really appreciate what Rudolph said, because often that's where I get engaged, right? Some agency, and it's often through the zero trust working group that we have, right? So there's forums where agencies get together to talk about solving challenges they have together. Zero trust is one of those areas, and CISA operates a group, 3 cohorts of people that get together and communicate about zero trust, and this is one of the topics we have. There's also the ICAM subcommittee, where all the agencies have ICAM people to get together, and this is not as much, but sometimes it's a topic there. Anyway, that we get together and talk about this, and I'm often helping people do exactly what Rudolph said, explaining to them how they get down into the tools that they have, determine if the tools can help them do basically 3 things, right? So in the network, there's communication that flows across that network, and that communication needs to be encrypted, and it usually uses asymmetric cryptography to begin that communication channel to make the encryption work, right? So you need to understand that cryptography. Let's go to the other area. Now look at your endpoints. The endpoints have things that are encrypted on it. You mentioned, losing a laptop, right? So people are really interested in on the device, what is secured, and then how does that get secured, and what cryptographic algorithms are used on it. it's a little bit technical, but some of the technologies that we use today, the symmetric cryptography is actually fairly resilient, and we'll use longer keys, but the same technology will be persistent, as far as we know, into the future, right? It is the asymmetric cryptography that we're going to be concerned with, and so that you have to learn about the differentiation between those two things, right? And then the final part, which may be a little harder, right, beyond the devices, is the government may have a fair amount of custom code that they developed, where inside those applications there has been developed some cryptographic algorithms that are not maybe standard, or maybe you really need to understand what's going on in there, and that is going to be a little bit harder. You have to open the kimono and see what's inside of those things. But those are the three kind of major pieces that we need, agencies to look at, and as they're trying to figure out what their cryptographic footprint is.
You just made it sound complicated. Charlotte, any thoughts on prioritizing the transition? And you could speak for GAO, but I also know GAO overlooks, the government in a very general way. So any way you want to take that.
Yeah, we'll go more general on this. So the big thing to think about here is time. This is definitely not the first cryptographic transition that we've done. We've heard a lot about SHA and the problems that were with SHA-1, and that took a long time, because even as of 2023, SHA-1 was not universally decommissioned. So these are not things that happen overnight. So along those lines, it's important to consider all the system dependencies, because when you transition a system, you're going to have to transition any system that gives that system data, or that receives data from that system, or from the network that transports that data. And this is going to be true across sectors as well. So it's something that's going to take time. It's going to take effort. Nothing here is going to happen overnight. So sooner we can start and get started on it, but of course not before the standards are released, and I think it was July, the better off we'll all be.
Very good. Dan, ideas about priorities, and you were kind of our, more like national security rep, so any kind of new wrinkles there?
As Dr. Hinkle just mentioned, this interoperability item is very important for what we do within the Marine Corps and the Department of Defense. If you look at it, every strategy, it's about using information to our advantage and preventing our adversary from having that same advantage. So we know that there's probably opportunities for our adversaries to stop us from being able to have that advantage, which then we have to look at what systems have we traditionally used where we have had that advantage. And those are ones where we have secure information going across some network or series of networks to do something. And you can imagine what those things are. The challenges, I think, are the challenges associated with doing this that helps to identify the priorities, right? Because you have to understand which systems support those missions of the organizations, and those then become the priority on the way we focus our attention. I mentioned earlier about that within the DoD, this situation has to occur, or the transition has to occur with a great deal of collaboration to ensure that everybody's kind of prioritizing in the sort of same direction, not just the general direction, but in timelines as well. And while it might be easy to put down on a timeline how you're going to prioritize these items, there are other issues associated with it. Many of you out there in the audience can have a role, which is the way these systems are developed and how they can be modernized. We have some systems that for various reasons they have to go into depot level maintenance or whatever to make those changes. Drives us to have changes that are in the decades, in the decades to do these things. And it's not so much the technology itself. I mean, we often fail, even though the technology is easy, and we say that this one, not only is it hard, and not only is the technology hard, but just the programmatics of it create a challenge as well. So we always prioritize against the mission, and then apply resources against those priorities.
Right. And Rudolph, you had said a few minutes ago felt like you were down in the weeds of some of this stuff. Is the view on prioritization sort of any different from that perspective, or are you kind of in agreement with the rest of the panelists?
Well, in general, I'm in agreement with most of the panel, with everybody. Like I said, I am down in the weeds, but we also have to remember that USDA may not be as glamorous as a financial institution or DoD or NIST, but they do very important work for the U.S. Farmers, ranchers, producers, and for international customers as well. We've got a farm bill that comes out every 4 years that dictates policy with regard to all kinds of information relative to farmers and subsidies and so forth, as well as technology, right? Use of technology, use of financial information. So, there's a lot of really important stuff going on there that needs to be really protected. And, we've got some great partners now that are doing it from my level down on the website level where I'm managing infrastructure for the websites. And while those don't host a lot of technical information or PII or anything like that, we do have a lot of information of a very confidential nature that is hosted on intranets and behind firewalls that we're really concerned with. This is data that goes to Wall Street for their use in making money off of government data. So yeah, I'm seeing all that. Although my purview is more the web domains and making sure those are all protected. I'm seeing the higher levels that we have challenges with from that standpoint. So it's a big challenge. I'm trying to get my arms around it, and I'm looking forward to the July dissemination of that information as well as the rest of USDA is.
Right. Just for the record, I consider breakfast, lunch, and dinner to be very glamorous. And so to the extent USDA helps that and US Food Supply, that's glamour, high up. So everything that everyone has just said, I had a next question lined up. It was sort of like, what are the challenges? And I think a lot of those things have probably come out. Is there anything, and this will just be an open question, anything kind of in the challenge department that you haven't quite touched on yet that needs touching on?
Sure. Hey, when you hear the words post-quantum, how much does that make you want to jump up and do something today? So it's a little bit the lexicon question. And the Q day is a word that people will say, what is Q day? Well, to me, Q day is the day that somebody has a crypto-analytically relevant quantum computer and is able to apply it to break somebody's asymmetric encryption, to learn what your private key is, and then therefore exploit your data. And so just why did NIST start a process in advance of these standards? Well, industry wanted to touch and feel and use the algorithms and start to identify where they fit well and where they won't fit. And then from the inventory point of view, since it hasn't been done before, it's going to take a couple years to roll this up. So the last 2 years, the non-national security part of government has been asked to do an inventory on paper. And if they were just lucky enough to have a little bit of money, they might have bought an inventory tool. But if they didn't, do it on paper. And it said, tell me about your high value assets. And then from that, can you tell me what encryption is protecting it? That's an interesting new game that they hadn't been playing much before, because before that it was, do I have a validated module? Because that's my requirement. So it's growing a conversation that we need to iterate on and learn from. And like the Marine Corps will be following the Navy will be following the DoD policy. The DoD policy is being led by NSA. NSA has agreed with this process that NIST started in 2016, that for their needs for asymmetric encryption, the NIST guidance and the NIST documents that become the standards are the ones that will inform the use of asymmetric encryption for the DoD. So there's a lot of good cooperation there, which means if you think your customers are all in the national security system, the relevance of the NIST work is strong and high, and NSA and CISA are partners in this project I'm talking about.
Okay. open question, just sort of remaining challenges people ought to know about.
So you touched on it, that, there's key establishment and there's digital signatures, and I think there's going to be discussions about what is going to be the appropriate algorithm for different uses, right? Some of these, you mentioned, Daniel, that there are some systems that take a very long time, that even if you wanted to start changing the day that the algorithms were approved, some of these firmware systems take a lot of time to go through the process to get them approved to be used in the places that they need to be approved to be used, right? So there's a lot of challenges in the timing, the planning, the specific use of these algorithms. And I think, and discovering what the correct digital signature is that we're going to use for the particular use of that digital signature. And this is not done with their evaluation of cryptographic algorithms, because there are others that have different characteristics than the one we've already approved, right? And I think those are all important, opportunities, but there are also challenges to kind of flesh all that out, right? And I think there's going to be, it'll take time and effort to do all this, and vendors that actually implement services that deliver these algorithms are going to have to, pay attention to the decisions they make and the recommendations they make for their particular products and which one of these to use.
Sure, go ahead, Dan.
I'll mention three items that I don't know have been touched on yet. One is the performance. Generally, quantum, I can imagine, will require a great deal greater performance than our current systems, legacy systems, would support, which really means upgrading a bunch of the legacy systems so that they can then use this capability. So that's one item, that just upgrading the legacy systems can make sure they work. One is scalability across the force. I sort of mentioned it when I talked about the interoperability, but the system has to be able to scale, and we do the entire force over some short period of time, which takes me to the third one. While it's not necessarily created because of the quantum problem, there's a system many of you would probably be surprised to hear that as we were upgrading, not we in the Marine Corps, but as the system was being upgraded because of a cryptologic problem, they had created this transition process that allowed them to deal with the changes in cryptology, the approach these ones using. But then it created a vulnerability across that system when it was being held by two different algorithms at the same time. Now that system is questionable as to the security of that one. So this security during the transition is something we should probably learn from as we try to put in place our transition plans to the newer state.
Great point there. Charlotte?
Yeah, I just want to add that just listening to this, we got to think about the costs. This isn't going to be free, and there may be systems that may need to be upgraded. So what are the costs going to be associated with this transition, and how are we going to budget and plan for it?
Huge point. Rudolph?
Yeah, I'll have to second that. I know that we're fighting for money for just basic software, today, and software that will, scan our services and our websites and so forth for vulnerabilities or for 508 compliance or whatever, and fighting to get that minuscule amount of money, and then considering that we have to upgrade our legacy systems, and USDA has quite a few legacy systems. We're trying to consolidate a lot of data stores and get into one big data warehouse where we can tap into that data. And we have a lot of competing interests, so it's a problem that we're having to deal with like everybody else, I guess.
Right, and I'll just stand in here for our host, Tom Suter, who had asked me right before we came up. He's like, hey, what about IT modernization and funding for that? And, that's as huge of an issue as it is today, but it's only going to get huger. So we're probably eating up a little bit of our remaining time. But I would be really remiss if I didn't ask in this room, which has a lot of industry presence, some thoughts about the value of collaboration, not only with industry, with academia, kind of anyone else. Maybe one thing that each of you would really want industry and academia to just kind of walk in the door and go, hey, let's do this, or let's talk about that, or let me add this into the mix? Open question.
I mean, I really think that, the NCCOE lab at NIST, is really reaching out to both industry and academia to help with this, you know, establishing the basis of what we're going to be doing, right? That's great. I really loved that you mentioned today about using the Zero Trust Lab to be able to then look at some of these endpoints that they've already have in place, because segmentation is really going to be critical to Zero Trust architectures, and the segmentation is probably going to rely on cryptographic algorithms to be done properly, right? So these things, so I think what I want to just say is that agencies should take a strategic view of all these different initiatives, because they give you opportunity, right? Modernization probably is going to, for most agencies, involve cloud transition. Cloud transition is probably going to be one of the means. That also is how you actually act upon a zero trust architecture. And both of those things can be, can enable what you're doing around modernizing your systems for cryptography, right? So these things just need to be thought about as much as you can together. And that's really difficult, right? Because there's a lot of moving parts and all that. But I mean, I would say that is a really key strategic function that agencies need to do, is make these things move together instead of moving at odds of each other.
Excellent. Any other sort of wishes of industry and academia? What can their best input be?
Yeah, I'll say I think some of the best thing that this country is known for is that collaboration amongst the three big partners, the academia, industry, and government, Department of Defense in particular. But I think we always win when we're doing that well. However, I would say in this case, it is very risky to be an early adopter in this thing without the standards being fully born and the solutions being mature enough to adopt. We have a saying in my office: if you adopt early, you generally adopt twice. So just keep that in mind.
Good one.
So a few big things to think about are how we can use things like partnerships and consortia and things like that, because partnerships and consortia can be helpful in identifying what is needed and can strategically organize different groups. However, it's important when thinking about these things to think about them beyond just basic research. They're oftentimes pre-competitive, and there are good reasons for them to be pre-competitive, but they should go beyond just that basic research aspect of things. And it's also important for partnerships and consortia to think about ways to help smaller companies to participate as well, because they may not have the resources that a lot of the bigger companies have that would normally work on these. And also to think about ways to strengthen connections between academia and industry. Because as we've been discussing our workforce, one of the ways that we can help strengthen the workforce is by strengthening those connections between academia and industry. Because if academia knows what industry is looking for, then academia can work to create graduates that have those skills that industry needs. But there are going to be challenges, of course, and we'd be amiss if we didn't discuss those, because it's important for companies to be able to protect their intellectual property. So it's important to balance that need for intellectual property protection with successful collaborations.
I'd throw in that I have a collaboration. It's a privilege to have and work with the folks who've already joined us and will be joining us. I'm happy to know, and I've been talking with the Cloud Security Alliance and their Quantum Safe Working Group. I'm really pleased to know that the Global System for Mobile Association has a post-quantum cryptography tech group, and they've put out a spectacular paper. So if you Google GSMA and use cases in February 22nd, you can read a paper that will be the most informative paper that you've read this week, because it will tell you use cases. It will describe them consistently in a way that says, here's stuff that we need to worry about. And in that public key infrastructure thing that it keeps being being thrown in front of you. Here's the thing within that this use case will require modernization of. And so there are other resources. The FSISAC has a PQC Congress. This is not a US only thing. My focus isn't on the federal government entirely, but I've been pulled into the federal conversations because the memo said do inventory, and we've got some inventory tools in our lab. So we're not the only game in town. There's a lot to Google here and learn about, or Bing if you want to do it that way, or just ChatGPT it, or OpenAI it, whatever. You can get some better answers now and inform yourself. You don't have to rush towards these things, but you can start today with things that have been learned by others and make some progress. And if you have that one person who loves to do inventories, they're going to be spectacular because they're going to want to teach 5 other people. And so the positive earlier about workforce is this is really kind of you're going to know the most about your stuff that you've ever known if you try to do a cryptographic inventory. And that's not a bad place to end up with your growing technology base.
Great tips. Rudolph, anything to add?
I would just second that, but I took the liberty to read through the NIST documentation in the last couple of days, and I was pretty impressed with the collaborative efforts that are ongoing with some of the big names, IBM, AWS, and so forth. And I found that great. And then I also saw that there were some small companies. There was a French company, French startup, and and that's what I think we need to do, because I know at USDA in general they advocate for small business, and I do as well. I like to have a small business come in, but sometimes they just don't have the depth and breadth of the large companies that and the resources to really take on the challenge. So, partnering amongst those is also a good thing. And I think, based on what I read, it's really moving in a great direction. So much work has been done in just the last 2 years. It's quite impressive.
Great. Tom, do we have any Q&A that we can entertain?
All right. What's your name and affiliation?
Hi, Lee Sattler with Verizon. And I've heard a lot of expressions of difficulty and pain associated with going forward with this PQC migration, and understanding that no cipher has survived the test of time. And at some point we might have to do this again. And I'm wondering if anybody on the panel has any thoughts about how to make it easier the next time as we're doing this now.
We haven't mentioned the term today, but one of the themes that we talk about is crypto agility, right? As we go through this process and learn how to update these algorithms, we should be prepared to be able to do that again, right? Because we do think that things are going to advance, and who knows what the future holds for us. We've been kind of moving in that direction for a while. The algorithms we have today, they tend to negotiate kind of what they need to do anyway. So we need to work about, how do we make sure that the algorithms do proper negotiation and limit to what you need to do, and just improve the agility we have in our environment.
Yeah, you know that we had a conversation 2-3 weeks ago on crypto agility to begin to ask and frame it in a way that for me would be going back to the collaborators and say, what can we build and do in the lab to demonstrate what agility could mean, what it ought to mean, and see if there's something we can do to measure that and demonstrate it. And then there's just going to be a little bit of level setting on the language that's necessary, so that when you get a push from some vendor here, you have a sense of what that's going to mean for you, whose technology stack and where in your technology stack they're going to make pushes. And that's going to require maybe some modernization to just what does it mean to have a valid algorithm running in a product. If you can swap things out, we're going to have to NIST, my colleagues at NIST, and they're going to make mad at me for saying this, as they modernize other standards around these PQC algorithms that are talking about asymmetric encryption, then the validation programs may need some updates to talk about, hey, what does it mean to be run in this mode, composite, hybrid, words that start to matter. And so it's a language definition, and there's some space to do experimentation.
More questions? Hang on, I'll be right over there.
Art, nice to hear you. So these new encryption paradigms are going to be much more robust to prevent against quantum, but much more robust running on classical computers, is going to be slower, I assume. I mean, is this, we're going to have a significant performance impact? Are we going to see serious degradation when these get implemented?
So yes, and that's why they want to do some measurements to prove out that what is the impact? What will you feel like as a user on a commodity computer in a corporate environment or at your home environment if you have good bandwidth? It does get trickier as you get down to bandwidth constrained environments. So that's the movement towards what's the use case where they fit and what else do we need to seek out in new algorithms. There are processes still ongoing in the crypto algorithm the standardization aspects. Continue to examine some new cryptographic algorithms for standardization for other use cases. So yes, and at the most recent 5th PQC standardization conference that NIST held, some of the folks came with, here's what I studied and what I learned, and the impact is lesser than I thought. Or, yep, we anticipated this and that's true. Bigger message sizes, bigger key sizes will have an impact. You said something very important. We're talking about algorithms that will run on today's silicon, tomorrow's silicon, the computers and the mobile devices we're using. And that is, a distinction. When I come to a quantum event, people want to sell me quantum stuff, and I'm like, no, we're still talking about algorithms that will work in today's stuff to protect against not only the quantum threat, but the existing threat to all crypto. And that's a big way to have the mathematicians figure out these could do that is pretty spectacular, but the mathematicians figure out how to make asymmetric encryption work in the first place. So yeah, we need to put all that information in front of people. Our test results are available, and when other companies do their testing, they're starting to share that information. I think in general is still, we're in the common good part of this space, this work.
The thought I had was, we're talking about quantum resistant computing right now. We use algorithms that we can use on classical computers, our current computers. But I think there's probably going to be, quantum-based cryptography, which in the future when you have quantum systems, right? The reason that I think that is likely is already, we talked about this earlier, already there are quantum random number generators, which are much better than any classical, digital system number generator, right? The best you can get with a digital system that runs on a crystal clock is a pseudo-random number generator, right? With a quantum random number generator, you can get really random numbers, and these are really important fundamental aspects of doing cryptography, is being able to do those things, and I think we'll see more of that as we develop more quantum capabilities.
Yeah, one last item that I'll add. I mentioned it earlier about the legacy system. Remember, us in the DoD, and I suspect other areas, we also have encrypted handheld radios that have to then also be able to operate in this environment. And many of them are already at the end of their performance life, and we're going to have to do something with those, which sort of goes back to your question about what better can industry do. Like with the radios, while it's a business system, every time we have to upgrade the firmware on those things, certain vendors will charge us a great deal of money to make those upgrades. So if you want to help the government, then do things a little more cheaply.
I'm going to offer an oversimplification. Make sure you have your risk management experts in these conversations too, because you might just be able to describe, hey, that bit of use of radio there, the data that was just transmitted is valuable for the next 25 minutes. There's not a CRQC that's going to break that in 26 minutes. So put that on the bottom list of things to modernize to PQC and keep using today's valid crypto. There's nothing being deprecated on the day these 3 standards hit the streets in July. You will still be able to do everything you're doing today. There will be a timeline to say when we'd like to see those algorithms that we're using today deprecated, and that's going to be one of those places where I imagine there's going to be some feedback. You said 20 whatever, NIST. Now let's argue about that. So that it's going to be proposals for deprecation and proposals for timelines, and that's where industry needs to come back in, and users need to come in and say, that's practical, or that's crazy, and then the economic part starts to weigh in too as you think about that, and that's a lot of people to bring into this conversation, but it's going to be vital and necessary.
More questions? Go ahead.
So anyway, good. So because I'm the moderator, I get to ask the last unanswerable zinger question, and you all have to try to answer it. The title of the panel is Getting Ready for Q Day. So I think it's fair to ask, even though there's no right answer, anyone's best view or any kind of pointers you want to point to try to shed some light on when will Q Day be?
Well, it depends on who you talk to. There are some people who say that a Q-Day quantum computer could be 10 years away. There are other people who say a Q-Day quantum computer could be 10 or 20 years away. And there are those who say it won't come. So it really depends on who you talk to.
I mean, when I'm talking to people, I use the term that we see in the OMB guidance, like, you need to prepare for general purpose use in 2035, right?
When I was asked to help co-lead this project, I just trusted that one will exist sometime before sometime.
I'll go ahead and say that they're working hard on it right now. Our adversaries are out there really working hard, and especially the Russians, the Chinese. They've got some really sharp intellectuals working in information technology. So I'm confident it's going to happen within 10 years or so.
Dan, your best guess?
Experts that are down there at this end of the table, so whatever they said.
Cool. Well, listen, I've learned a lot. I hope everyone else has too. I appreciate the panelists.
Great panel. Thank you, John, for moderating. You always put a lot of work into it. I definitely appreciate it. We're almost there for lunch, but we got a couple. We got Allison Schwartz, who's going to put a little pitch in from our quantum working group. And Allison, I don't usually start groups. I always start groups. I need to have a good leader, and Allison's just been a fantastic leader. And you got to keep an eye on her. She's at Capitol Hill. She's here. She's there. She's everywhere. But she's going to talk a little bit about the activities in our quantum group before we go to lunch.
Thanks, Tom. Thanks, everybody. There we go. I'll turn it on. Thanks, Tom. Thanks, everybody. I'm a New Yorker, so usually I don't use microphones because everybody can hear me regardless. As Tom said, I am the industry co-chair of the ATARC Quantum Working Group. I'm also a global government relations leader at a company called D-Wave, which is a quantum computing company. And I came to the company about 4 years ago, and one of my first things I did was get involved with ATARC. And I was wondering kind of who would be talking about quantum in the government at that stage. Is it too early? Is it not? And seeing this packed room today, knowing the amount of people that are online as well, there's one person who actually told me that there's going to be a thirst and a hunger for this. And so thank you, Tom, and the ATARC leadership for creating the ATARC Global Quantum Working Group, because it really has been a way to pull academia, government, industry together, and also international players. I want to thank Tim Harvey at ATARC for his work on helping get such robust engagement from the government perspective. And we have two amazing people who are helping us with the working group itself, Amy and Elizabeth, and thank you all for your hard work. I would be remiss if I also didn't thank my government co-chairs. Unfortunately, they're not able to be in the room today, but Lily Chen with NIST, you just heard a bunch of the work that's happening at NIST on post-quantum cryptography. She and her team are leading a lot of that and helping the working group understand better what's happening, and Jason Lee from GAO. And a lot of the implementation, once the post-quantum cryptography comes out, obviously will be implemented from a GAO standard perspective. So thank you both for your partnership and collaboration in this effort. So many of you may not even know that there was a Global Quantum Working Group. I do see some of you folks that I see on our working group meeting, so thank you. So who are we? ATARC, as we've mentioned, brings together academics, industry, governments, and that's what this working group does. And so we share news about current events. We share news about what's happening globally, because quantum is a global race. There were questions about spending in China. So let me just throw a little stats out for you.
The global spend in 2023, which obviously we're in mid-2024, so there's more, was $38.6 billion. Of that, China spent $15 billion, and the US was under 4. And if you look at some of our allies, they are either around or below what we spend in the US. And so it's understanding that there are huge amount of effort in this space, and we have to figure out how we in the US, but also with our ally partners, can actually build the right technology, identify the right use cases, provide the opportunities to protect our encryptions. We cover a variety of different quantum technologies. So you've heard today about quantum computing. You've heard a little bit about quantum sensing. Hopefully in next panel, PQC efforts, hopefully in future panels, you're going to hear a little bit about quantum communications and quantum networking, and there's quantum hybrid applications. All of these are included in the work that we do within the working group, because we understand quantum is kind of this big word that nobody really understands and should be cool. Sometimes it's scary, as we heard earlier. Who engages? So as I mentioned, government. So we have folks that attend our working groups from Homeland Security side, national security side, defense, intelligence. We also have the civilian agencies. We have third-party policy organizations. We have academics, government contracting organizations, industry, national labs, international, as I mentioned. Every person is on their own journey through their quantum realm. So do not be afraid to come and engage if you don't feel like you're an expert. We have folks that are steeped in only one kind of quantum technology. We have folks that have no idea about quantum technology. As I said, I came to quantum 4 years ago. Before that, I was in fintech. So I've been on a huge learning curve. And I agree with the comment mentioned earlier that the coolest thing about quantum is you're never going to learn it all. So there's always something new to learn each day. One thing that we realized was we needed to have focused goals. So we picked 3 goals. Goal number 1, education. Goal number 2, education. Goal number 3, education. And because there's so much uncertainty and doubt. So the first education is the technology. What actually is it? What can it do? When can it do it? You've heard a variety of different timelines for PQC. You've heard a variety of different conversations in the first panel. And so we really want to demystify the technology and better understand it and provide a little insight of what is quantum information science. There are different modalities of quantum computing. There are different types of technologies within quantum sensing. We use the terms as holistic and monolithic, but they're really not. Second education is on policy initiatives. As I mentioned, there's a huge amount of governments engaged. As a matter of fact, 17 governments have quantum initiatives and quantum programs. The US has cooperation agreements with almost a dozen of those. Now, the issue is, if you look at these bilateral agreements and you look at the quantum industry, no one government, no one region of the globe actually has the entire supply chain for any quantum technology. So we have to do this from an international perspective. And that's why we wanted to make sure the international working group actually had folks come in. The last one is, who and what is doing it in the industry. Folks know the big names, Microsoft and Google. You have Sandbox AQ, D-Wave. You have other folks that are not as well known. So we tackled this in a couple ways. One, we created a quantum speaker series. Several of the folks you've heard speak today have been part of it, so thank you. And if you don't have it, you can go up in the registration area. I think I can advance the slide. If not, it's fine. There you go. The Quantum Speaker Series, we have speakers that come from national laboratories. We've had Oak Ridge. We've had Purdue University come and talk about Center for Quantum Technologies. We've had government agencies come and discuss work that they're doing, industry as well. Again, we're trying to break down the barriers, and we do provide these virtual. So it allows access for everybody, so you don't have to be in the DC area. Although I do love seeing everybody outside of the little boxes today. Another area in which we're educating is through white papers. So we had, in fiscal year 21 NDAA, there was a task to DoD to create lists of problems they wanted to solve with quantum computers in 1 to 3 years. So ATARC was the first to create a white paper for applied quantum computing for today's military. That came out in 2021. Now there's actually legislation to create pilot programs and applications development that go beyond computing, including sensing. And so that's really exciting to see that ATARC was kind of the leader in that. We also have one that's on an quantum safe framework. So this is an inter and intra-agency way in which to become quantum ready. These are all available online. We also have a few copies left in the back. And this was actually created by the working group, and it looked at how to provide guidance and standards, how to share information, how to do things through public-private partnerships, which you've heard a lot about. The last one that we're working on currently, we took on the audacious task of trying to figure out how to demystify the technology as a whole. And we realized we couldn't really do that without getting a huge book of 900 pages. So we decided to take it in chapters. And so chapter 1 is out, March 2024 it came out. It was looking at quantum computing and post-quantum cryptography, again, available on the ATARC website. And then we have chapter 2 coming out soon on quantum sensing. And so we'll be doing other chapters on the other types of quantum technologies as well. A lot of the quantum speaker series are on the ATARC YouTube web channel. And the one thing I will ask is if you are interested in learning about the working group, want to get more involved, talk to any of the ATARC folks, talk to myself. We would love to have you there. They're virtual meetings once a month, and we want you to attend, whether you're an expert in quantum, only care about one specific area, or just want to learn. And I'm happy to answer any questions. I know it's really bad to be between people and food, so I will try and make it short.
You're good. I don't think lunch is just about ready.
Okay.
So any questions? Yeah. Thank you for your leadership. I forget all the things we've done, you've done with this group. A lot of work put out there. Next year, we're going to have a quantum book that we'll kind of have, as a handout if anybody wants to sponsor it. I was just thinking, we're actually making a book.
Yeah.
You and your team. So
We are doing the chapters, and I just was editing the quantum sensing chapter, and I'm a quantum computing company, so it's outside of my scope of expertise. And it's amazing the amount of work that's going on in Korea and China and Europe on patents for quantum sensing. And the US leads in patents for computing, but not in the other quantum technologies. And so it's really very interesting. I forgot to mention, we do have for folks to register for on June 4th next week, our next quantum speaker series will be AWS. They're going to be talking about a result that they have gotten on algorithms. So please sign up. Again, it's virtual, and we would love to have you.
thank you, Allison.
Thank
Round
you.
of applause for her leadership. We actually have another working group representative. We just recruited her from the speaker room, and she's going to talk about Dr. Amy Hamilton. She's a very interesting lady. She works for the Department of Energy, but she's on detail to NDU or something. I don't know if it's actually a detail. I don't know how you do it, but Amy's running our Zero Trust Working Group, and she's going to just spend a couple minutes just talking about that, and we get some quantum types of things we're going to be working on too. So thank you, Amy.
Perfect. Thank you so much. And I prepared nothing, so it's kind of like when I teach class, right? So it's going to be fun. So I do want to just thank Tom and the entire ATARC team because they allow us to have this forum. And it's really this amazing opportunity. I'm with the government, Department of Energy / National Defense University, College of Information and Cyberspace. So it's honestly the coolest thing I've ever done in my life. And I've been with ATARC at the Zero Trust Working Group for about 3 years. And that was when Executive Order 14028 came out. And that was honestly 3 years ago, in May 21st, 3 years ago. And suddenly it was Zero Trust was on everybody's lips, and everybody was talking about Zero Trust. And as we did Zero Trust, we created a lab series. And at first it was sort of hey, everybody bring your Zero Trust. And you see this in quantum now. Everyone's bring your quantum. I've got quantum everything. And you're what exactly does this word mean? Does this word mean what you think it means, right? So we start questioning that. So same with Zero Trust, same with AI, right? These are kind of the three big buzzwords. So as we went through our Zero Trust Lab Series 1, it was sort of what do you have that's Zero Trust? When we did our Zero Trust Lab Series 2, we had a very defined set of use cases. That's what we're in the process of now. And the use cases goes through all the pillars of Zero Trust and all the steps. If you're using the CISA model, if you're using DoD model, it's just pillars. DoD has no governance. I use that as a joke with my DoD colleagues. So very interesting in their model. So as we look at it, you look at the zero trust, and then we said, okay, what are the areas of zero trust that's kind of niche use cases, things that like we were like, we should be including these, and these are hard. And so we have quantum as one of those. We have AI as one of those. We have multi-cloud in there. We have metrics, because metrics are like the worst. One of the other cool things that's come up in zero trust is training. When we first started looking at zero trust training, there was like one basic company offering it. Now you see a lot of other organizations offering zero trust training as well. And so one of the big ones that's close to my heart as a Department of Energy person at heart is operational technology. And when you really look at that nexus point of cybersecurity into the physical world, and you're like, this is a lot of zero trust talk at a quantum summit. So what are you really getting to? All of these things are inherently and intrinsically intertwined at this point. And I was talking to someone this morning, and I'm like, remember back in the day when the coolest thing in the world was when we were going to be able to store a terabyte of data? I mean, you look back now and you're like, oh, that was cute, right? And if you look at where we are in technology now, we absolutely and fundamentally have to shift our thought processes and realize that the tech is coming faster and in ways that is harder to understand. And so I love to read about quantum, and then I go back to the fundamental concept, and I'm like, okay, so bits, we all learned this back in basic computer programming, zeros and ones, and then I learned kids today don't know computer programming, they just have computers. 39% of infants have access to a smartphone on a regular basis. That's 0 to 2-year-olds. That keeps me awake at night as well. So random statistic for you to know and like be afraid of. But when you really think about the fundamentals, 0 and 1, right? It exists, it's easy. As a logic person, I get this. When I think about qubit, and now I have a 0 and a 1 that can exist at 2 separate states, and then it makes me think about Wrinkle in Time and having to read that in elementary school or junior high school, and I never quite understood it. And I feel like that's always where I'm at with quantum. I'm almost understanding it, and then I just watch old Star Trek episodes and feel better about myself. So I highly encourage you to participate in our quantum working groups, absolutely wonderful part of ATARC. We also have many of the other ones, and I wanted to highlight our Zero Trust in-person summit is October 3rd. It is going to be pretty incredible, and right now, if you're following anything in tech, what I would do is AI/machine learning. I would follow along when it comes to everything quantum. And why does zero trust matter? Because inherently and fundamentally, we have to make sure we can secure these things. And defense in depth never worked. Perimeters did not work. And the more that we are in an integrated society, the more you have to look at cyber physical engineering from day one. I don't know if anyone's tracking what's going on with the EVs. It was super great. Let's have this new technology. Let's roll out a whole bunch of cars, have them hook up into electric systems, which also then become cybersecurity vulnerability points where everybody can steal all of your information. And it's like this super fun place for the hackers to go now, where they can then take your credit card information directly off of where you're charging on a public EV. So that's just one example of the many, many places where people don't consider cyber as they're developing new tech. And that's where your cybersecurity person comes in. And then we have to have all these things come together. And I'm looking for Tom to give a sign. Are we ready for lunch?
I think we're ready. That was a good way. Now we're all real hungry. That's good. Thank you. Thank you, Amy. Appreciate that. Once again, I'd like to thank all of our partners that have participated. We're really early and, in this journey that we're in. But anyway, lunch is served. You don't have to run up there and get it. We haven't run out of lunch yet at this summit. So you don't have to be like first with the mostest. And we'll get together at 1 o'clock. But Amy's up here if you want to, or my team or anybody during the course of the day, if you want to find out more about any of the working groups, we'll hook you up. But that's where the action is. So anyway, that closes the morning session, and we'll see you all here at 1 o'clock.
Welcome to the panel on quantum connections and how quantum interacts with other technologies, such as cybersecurity. I'd like to introduce the panelists. To my left here is Dr. Michael Haydup. He's the Deputy Director, Information Directorate with the Air Force Research Lab. Next to Michael, it's Dr. Amy Hamilton. Chair of the National Defense University, U.S. Department of Defense. Next, we have Sherry Thomas, the Cyber Technology Officer, U.S. Marine Corps Forces, Cyberspace Command, U.S. Marine Corps. And next to him, at the end of the table, Dr. Robert Campbell, the Quantum Safe Executive with IBM. So thank you. Thank you for joining us this afternoon. You know, quantum computers have the ability to process complex computations much faster than conventional computers, that offering real benefits to society, from optimizing finance to really ushering in new developments with personalized medicines. But there's that one thing there that it also has the ability to really break many common forms of encryption, and strong encryption is the foundation of safety, trust, privacy, and our competitiveness across the digital economy. And in the words of the federal CIO, Claire Martorana, it unlocks innovation by securing it. So with that in mind, I would like to start with the question of how does quantum technology redefine the concept of security in cyberspace? And Michael, do you want to start?
Sure, be happy to jump in on the first one. So, speaking here from the Air Force perspective at AFRL. So just a little background, we have a program in quantum information science across the AFRL enterprise that spans 4 key areas: timing, sensing, networking and communications, and then finally computing. On the computing side, we're not building hardware in-house within AFRL. Instead, we're leveraging what's out there in the commercial world, and we have signed partnerships with commercial providers such as IBM and INQ. So that's given us a good start in terms of what we can do with a quantum computer in the Air Force, and we're looking at problems that are very typical. That I talked about how to enhance machine learning using quantum optimization type problems, which is imagine would be of huge interest to the Air Force, and then certainly quantum simulation. How we can develop things like better materials, better airplane frames, things along those lines. So certainly on the security piece of it, though, we're closely following, and we heard a great panel session earlier, a couple great panel sessions on where post-quantum cryptography is going, the NIST standards that'll be out. We heard published very soon and out for use. So we'll be certainly using those, leveraging those. I mentioned those use cases for quantum in the Air Force. We're not looking at encryption pieces and how to break encryption, but how we kind of really, if you were to break it down, the big data type problem as well. So security is always of interest to us. Where we're really looking at security, in addition to just implementing algorithms down the line for our Air Force systems, would be on the quantum side. I think we'll talk about later on, but more quantum networking and how we could use quantum communications to our advantage for security.
Thank you. And Amy?
Thank you. And I kind of want to look a little bit at the history of the internet a little bit here. So if you look at ARPANET, which was sort of the very earliest kind of connected computers, which then led to NSFNet, which eventually led to the internet being shared kind of across the global community, the whole concept was not having security. And so it was a very, very different premise. So you have the foundation that was designed to not be secure. And then there was a certain point, and it really comes into when a British scientist over at CERN said, hey, let's do this thing. It's going to be the World Wide Web. And from the World Wide Web, we're going to start doing e-commerce. The first thing that was sold was actually a Sting CD, which is sort of fascinating. And so when you look at the history of the internet, it was very much designed to be open communication, research. This is a research organization. And what do researchers want to do? We just want to share information. We want to just kind of geek out with each other. If you look at the first cyber attacks, it was still like a bunch of people like playing pranks on each other, if you will, right? It was supposed to be fairly harmless. Nobody had any malintent. At the same time, nobody could conceptualize, like in the 1960s and 70s, and even the 80s to a point, that this would become this global phenomenon where suddenly we're all dependent on it. And so right now, as we move into this world of quantum and you're looking at this whole concept of the data smash and grab, we're going to take your data now and decrypt it later. It's a very scary world. But just as a reminder to those who may or may not have lived through this, but we all lived through Y2K. Does anybody remember when all the planes were going to fall out of the sky and we're all going to die? That was kind of exciting times, right? And everybody had these Y2K teams, right? And we're all planning on like what was going to happen. But then what happened is really, it was kind of a big letdown. And probably the biggest thing that people could not figure out is if you had already had your tombstone and it said 19 ... and it was just like spaced. Yeah, fixing that marble, that was expensive, right? But when it came to actual technology, we figured it out pretty quickly. So people should not be terrified of quantum. They should be aware of quantum, right? And that's really what we want to make sure is you're aware is the next evolution. And just like when I was in 1994 as an Army lieutenant with my screaming bit rate of 512 kilobit per second, off of back of three Humvees, that was like super fast back at that time. 30 years later, you laugh at this, you giggle, right? And so technology will evolve. Quantum is going to evolve. Everything that we've been talking about, the quantum networking, the quantum computing, the fact that we're having our first post-quantum algorithms, these are very, very important milestones, but we have to not shy away from them and be ready for all of this coming down the pipe.
Sherry, before the panel, you said that you are all about operationalizing quantum and other technologies. So can you talk about that?
Yes, absolutely. First of all, ATARC and this forum, thanks for having me. Sherry Thomas here. I'm the Cyber Technology Officer, multiple different hats. But basically, we are the operational arm for the Marine Corps in terms of cyberspace operations, offensive, defensive cyberspace, space operations, space-enabled cyber operations, and we do some special exquisite mission areas too in various different AORs. You probably can see in the news what's happening in the CENTCOM theater and the Indo-PACOM theater. Discuss that in other forums. Back to Tom, the music is nostalgic in the 1980s, but as Amy mentioned, right, we got to keep up with technology. We don't want the 1980s technology. We got to keep up with it, right? The hardware and the software, it has to be tied together. Where I look at it is my brethren, my friends that sit across the street from me are US Cybercom headquarters and NSA. NSA's job is to break code, right? We use all of that and tighten up our networks, right? The defense in-depth strategies, the defense in-depth posture, multiple different things that we're looking at, zero trust initiatives and cloud computing and all these things to make the network harder. Now we got this new thing that we got coming up, right? Quantum computing. It's got to change the entire paradigm of how we're operating, right? Both hardware and software wise. So need a lot of different things, right? From partnerships between nation states, partnerships within industry and academia partners that are out here. And what I would say is it's got to be a whole of government approach, right? Was already mentioned, the federal CIO made that comment. So that means the entirety of the federal government. What we're looking at from the DoD lens is the PFMO for Zero Trust, Randy Resnick up at the DoD CIO level, is looking in terms of cybersecurity, and one of those is zero trust across all of our pillars, right? Every single thing that we touch, feel, see is something that's connected to an integrated chip or something with low computing power to large big data that's going up from every one of our devices out here to the cloud, to somebody's cloud. Somebody owns it, right? Do we trust all of that? Do we have confidence in all of that? When we lose the confidence, then we have problems, right? So that's what we got to look at in terms of things down the horizon are the quantum computing, but then to get ahead of it is the post-computing architecture that we need to be looking at it from a cybersecurity lens, because if not, we're going to have a plethora of problems. My other concern is I can protect my network, but then if somebody else is not protecting their network, they're going to get into my other enemies or adversaries are going to get into that and then do lateral movement into my network. Most people here should be tracking Volt Typhoon and different things that are going on in the cyberspace, right? Home routers and how you can get into various other networks with that. I'll keep it there because CISA has a lot more information DHS, right? These are these partnerships that we need to be working on between all of us that are out here and the larger community that we all interface with on our devices daily too. I'll add more as we go along. Thank you.
And Robert, nice tie, by the way. I got rid of mine, but if I had that one, I would have kept, kept it on.
Thank you, thank you. Let's see, this is a very exciting time for me. I just love technology, and I'm going to date myself a little bit. My first courses in programming languages were like Fortran, COBOL, and we had University of Maryland. We had an IBM 360. It had 64 megs of memory, if I think. Maybe that's a little bit high. I'm talking about megabytes, not gigabytes. It was able to do 34,000 instructions per second, right? This is a big mainframe, and it took up a lot of space. And so as a programmer student, I had punch cards, right? These little paper cards that you punch the instructions in, and you stack them up, and we had to give them to the operator. Come back the next day, of course, the program didn't work. But that's where we've come from, right? We from that place to where we are now, and IBM again is leading the way in terms of quantum computing. We're making great unexpected breakthroughs in quantum computing. Now, one other technology I think that really can't be separated from when we talk about quantum computing is artificial intelligence. I had my first course like in 1992. I said, oh, that's interesting, but we didn't have the compute power to make a difference, right? It's like, it just required a lot of resources. That's not the issue anymore. It is, now we got to think about quantum-powered artificial intelligence. What does that mean? How does that threaten, or how does that transform everything that we do? So we have two technologies here that are transforming the planet. And I particularly work in the quantum safe or quantum research group, working on the algorithms that will most likely be announced here shortly by NIST. And IBM is a major contributor to 3 of the 4 algorithms that are going to be standardized. So having said that, I think it's difficult for the average person to understand what we're talking about here when we have to change out the cryptography. As the good doctor here talked about, how you think about the internet, how it came along. We had PKI before we had the internet. Internet came, and we started to put cryptography on the PKI system to protect online transactions. Well, we had to look at cryptography is nothing that we had to worry about before, right? We had some upgrades, advanced encryption standard. It took 10 to 15 years to, by the way, to adopt that fully. And then we had another upgrade, SHA-1 and SHA-2, which is a hash function. It took 10 to 15 years to adopt it. Now, what we're talking about is something much more complicated, much more pervasive, much more massive when we say public key cryptography. When we say public key cryptography, basically think about everything you do in cyberspace, everything that you do. That's public key cryptography. That's the protection that you have. Whether you're going to your banking home page, anything you do online, any kind of secrecy, any kind of digital documents is protected by public key cryptography. All of that has to be changed. And we've never had to do that before. So it's a major education campaign that we are embarking upon to kind of get the word out. Hey, this is really, really complex. This is really, really big. We've really never done it before. and it has significant consequences if we don't do it right. So anyway,
Yes, we're going to come back to that and the complexity and the whole aspect of changing, have to change the cryptography. But I want to focus on the area of sort of the interconnectedness of especially with cybersecurity these days. And you brought up, Sherry brought up zero trust. Robbie brought up AI. And I'm wondering now with the, how does quantum fit into these new technologies as well as the new cybersecurity frameworks? And I'm going to start with Amy here because you talked about zero trust, and it all has to work together. AI, zero trust, the cloud, quantum.
Perfect. Thank you so much. And for those of you who are not here before lunchtime, I have the pleasure of being the ATARC Zero Trust Working Group chair from the government. And so if you are interested at all, please let those manning the reception know. We can make sure you get on the proper mailing list. And one of the things that we've been looking at very closely in Zero Trust, and it kind of goes to the foundation of EO 14028, which was you must encrypt the data to the maximum extent possible, right? And so the interesting thing is, what does that mean right now? It goes back into Shor's algorithm. But what do we have to do is change it. And so it was very interesting. The Office of Management and Budget issued a memo for post-quantum. And it's really kind of fascinating because most of the time, and I love my friends at OMB, but they're not very proactive, right? It's normally like a very reactive thing, like something happens and then they come out with a memo. So the fact that they said, hey, you need to look at post-quantum and you need to identify all of your devices before quantum's even out, that should signal to everyone the significance of this, right? I mean, this is pretty unprecedented that we're doing something proactively. So it's identified, all the agencies had to go out, they started doing their inventories, we've had to do the prioritization. And one of my favorite things about it is they also said, and how much is it gonna cost? Well, I don't know how much the future is going to cost. So if anybody knows that and you guys can predict that, that I think is going to be pretty interesting. But when you look at the fundamental part, though, is how do we protect the data? And networks exist for the data. Computing exists because we want to get information. If you look at what is AI doing, AI is creating data at an exponential rate. And so if you look at the fact that you run AI then creates inference data, then we need more storage, and then it becomes a circle, and then you have more data that you have to protect. So when you're looking at why does this matter to zero trust principles are all based on the fact of minimizing the impact of breach. So first of all, there's the assumption that you are compromised. This is a world that we live in, right? Like you are compromised. This is something very, very easy to do. But how do we minimize this? And this goes into you minimize it by microsegmentation, you minimize it by encryption, you minimize it by ensuring that you have good phishing resistant credentials in your identity, that you're looking at device authentication as well as user authentication, et cetera. I mean, there's all kinds of things that we're doing in cybersecurity to make sure it's to the most granular level possible so that when that breach occurs, it has the most minimal impact and we can recover fastest. And the most significant thing on this I want to really just highlight is supply chain and cyber from inception, that cyber-informed engineering. I love talking to engineers because I have no idea what they say half the time. And that's kind of true though. I mean, so you do, you sit with the engineers as a cybersecurity person and they don't understand what you say. But if you can be there in the room during those early concept phases, it's very changing. And what I will say is working with the scientists right now as they're developing the quantum technologies, the cyber teams need to be there from the beginning. And if you are working on quantum and you're not including your cyber team, you're doing everyone a disservice. And so that's a little public service announcement there. But the really important thing is that we're all at the table talking because all of these new technologies are going to enable and empower our lives in ways that we can't imagine, just like we couldn't imagine 30 years ago how the internet was going to be impacting us, that you can no longer hail a cab on the street anymore.
Michael, I saw your head nod when I mentioned the cloud. So maybe this next can you also answer this question, about how quantum will, what are the challenges you face in putting quantum into these new cybersecurity frameworks as well as technologies?
Right. So, yeah, I really resonate with what Amy said too about, building in the cyber protection right from the start, right? We have several programs in the Air Force where we're actually looking at, hardware, software, root of trust, how we can bake that right in from the beginning, so not just layering on things. So, I think with quantum, we definitely resonate as well to think about it early on as well. What impacts will quantum have, right, in terms of breaking encryption, but then how do we protect the information as well? How can we then use it to our advantage as well? So definitely, when we look at things in the Air Force, certainly how we protect our networks, of course, it's all about the data, but what other things can we do? And so certainly when I think about that and think about the science aspect and the engineering aspect would be things like quantum entanglement, how we can push security up a layer. So going even beyond quantum key distribution and what's out there. So the Air Force, we're not looking at quantum key distribution per se, but looking at entanglement and the added layer and levels of security that they may possibly bring, right? So it's not a guarantee right now. That's one of the things we always have to do is make sure we're countering the hype as well. But certainly where we see security coming into play in the quantum world is definitely in quantum networks and in the applications that it could bring, such as tying together new quantum sensors for GPS denied environments or higher precision clocks, being able to distribute apertures of interest, and certainly distributed quantum computing, which I think will be our first play there as well.
And Sherry, I see you taking notes there, so I know you're probably chomping at the bit to say something about the interconnectedness of all these technologies and zero trust you mentioned, and which is really about principles, right? And rather than technologies per se. But what are your thoughts?
Sure. Couple of basic things, right? Service members from either the Air Force, the defense level, from any of the services. Our basic job is to protect the nation, right? We're not protecting the network. We're not protecting technology. That should be inherited. But with the pace of technology change, we got to keep up with that too, right? What we're doing from the cyberspace command perspective is we're fighting the network and fighting the installation every day. And that systems that was mentioned, right, is system of systems. Everything is tied together, right? So the power and energy grid up here, right, we're assuming that is there so we can have our devices. And those devices are connected to some network that's out there. And there's a backup, right, PACE plan, preliminary, alternate, contingency, emergency plan. So if something goes down, there's a backup mechanism for it. Are we all prepared for that? In any kind of contingency environment, in competition, crisis, or conflict, right? Various different scenarios. And then, as Amy was mentioning, like the lateral movement in the network, right? The basics of that zero trust is three to me. One is the user, every single user, and that user is connecting to a device, whatever that device is, right? It could be one of these end user devices, but it could also be that the IT person that's touching the router or the switch, still a user connecting to a device. And then from the device to a software application, some kind of software application, a basic app or something at a higher level that somebody needs extra credentials to get to. Are we securing the entirety of that framework? If not, there's problems, right? And there's once you get in, you can move into other areas of that, right? That can be as simple as a home router at home, where it's not just a simple function of getting access to that, but then what else can be done once it gets in, because everybody's on a 365 or some kind of environment where you can get into other areas from work from home or other scenarios, right? Now I got to think about what's the data, right, that you can get access to, and how can you bring it down or move it over, all those external areas, right? From the operational side, we have multiple things going on. We have cyber protection teams. Their purpose in life is to protect the network. And I don't say just the Marine Corps network or the DoD network. Any network that we see has vulnerabilities or has issues, how do we get that to a better posture, right? And then now you add in a layer of quantum computing, and now you got to figure out, hey, do I need to switch out hardware? Do I need to take the cryptography or the cryptology to another level that we have not thought of? And then now you have to re-architect the entirety of it. What is the time frame for that? And can you keep up with the adversary or the threat? And then cyber rotational forces. They are constantly rotating in and out and trying to figure out different areas into the network where there are problems, right? And I say network, right? Network of networks, systems, because yeah, in the DoD writ large, multiple different organizations, Air Force and Army and Navy included, we're all looking at a singular network. We're bringing together a lot of tactical networks, enterprise networks, and saying from a zero trust lens, right? If there is an event that happens, are we able to cordon off or containerize that certain set of the information, right? SIEM and SOAR capabilities, security incident event management, security orchestration and response. How do you respond to it quickly so that the rest of the mission, everybody else doesn't have a problem, but maybe one corner of the room gets segregated out until they remedy themselves, right? And that's got to be that autonomous way of remedying instead of you guys trying to figure out how to fix the network, because that might not have enough access to. So the totality of it. And then going back to something that was mentioned earlier too. The entirety of the population has to be aware of what's going on, right? I'm looking at it from a .mil PF perspective. Doctrine, organization, training. It's not just a material solution. Yeah, we always have good ideas and new technology that comes out, but then how do you incorporate it into the whole thing? The leadership, the personnel, and the facilities, right? It's got to all be aligned so that we figure out from end to end, right? It's not just acquisition, for example, just buying new stuff, but how do you do the appropriate R&D to incorporate into the systems, the procurement, and then the sustainment tail is a large piece of it, right? Almost everything that we touch is more than 80% sustainment. We're going to keep our phones for a while, right? Or our devices for a while. And then you have to figure out, like, what is the alignment or the velocity, or how can you get rid of it? What's the plan to get rid of it, and how do you assume something new, right? We're talking about post-computing, but not the entire world can switch overnight. There's going to be a time phase approach. So we've got to figure that out and stay ahead of the curve of, falling behind too. Thanks.
Oh, yeah, this, there's something very fundamental that I want to discuss here. First of all, when we talk about post-quantum cryptography, we're talking about algorithms that will run on your current computers. They don't run on quantum computers. We're talking about post-quantum. But you may hear the term quantum cryptography, which is different. It's a different science. Quantum cryptography is based on quantum mechanics. Post-quantum algorithms are based on mathematics. Another thing is that is really important. When we talk about cryptography makes cybersecurity possible, right? So if you don't have cryptography that's safe, or if it's broken, then it is not possible to have cybersecurity, not possible, because the cryptography enables cybersecurity. Now, we have mandates going on. Of course, everyone will be migrating to post-quantum cryptography, right? And then, so what we'll do, we'll institute, deploy, implement these algorithms. These algorithms are nothing like we've ever used before in many respects. So it's going to change the paradigm and how we approach and look at cybersecurity in general. Now, unfortunately, we've hyper-specialized. We say cryptography over here, we say cybersecurity over here. They should not be separated. You can't have cybersecurity without cryptography. Now, if you're talking about the foundation being cryptography, so when you attempt to build, or you build on top of the foundation, if that foundation has to be changed, then there may be issues that come about that may be difficult to rectify later. So for example, You know, it's just your, the foundation of your house. You don't want to build on that knowing that your foundation is going to have to change. So again, fundamentally, cryptography is the foundation of cybersecurity. So any type of cybersecurity scheme that you have to put on top of that, recognize the fact that if it's not post-quantum, it's going to have to be changed. And if it has to be changed, it means that I'll have to dismantle that system to put in post-quantum and then try to put the pieces back together. That's what you call cybersecurity. And it's not likely going to work. So I just wanted to make sure that that was clear. And the reason why it's not clear, again, I mean, most people aren't cryptographers. I mean, we never had to talk about this like we're talking about it now. But everyone needs to be on the same page and understand that.
Okay, I'd like to stay with you for a minute there, Robert. In what ways does quantum computing, pose a threat to traditional encryption methods, and can quantum cryptography, truly guarantee unbreakable encryption? And what are the limitations?
Okay, so for what we call classical cryptography is what we're using now. It totally breaks it, right? So, you hear about, well, when will that be? What year? I don't know if those are good arguments to even have. First of all, you've got harvest now, decrypt later, all right? So if I don't have a quantum computer that's capable of breaking your cryptography, I expect I will, maybe a few years down the road. And especially if you're in the business of keeping information, digital secrets classified or secret for 5 years, 10 years, 20 years, sometime a lifetime, then you have to be concerned about it right now. Secondly, not only does it break our classical encryption totally, again, we can't separate quantum computing from artificial intelligence. We are combining the two technologies together to look at breaking cryptography, right? So we don't no longer need some astronomical number of quantum bits to be able to break today's classical cryptography. We use machine learning, deep learning, along with artificial intelligence combined with quantum computing, and we have a new power that we haven't seen before. So, I think that the time is now to make a move in terms of migration. And you said something about whether it's truly unbreakable. When you say quantum cryptography, are you talking about quantum mechanical principles like quantum cryptography, QKD, that sort of thing?
Yes.
Oh, okay. Well, so there has never been a cryptography technique that can't be broken. There is not one today, and there will not ever be one that can't be broken. In QKD, there are many attacks you can do: laser attacks, fake trusted partner attacks, many types of attacks. But the key is you move away from information theoretic. When you talk about quantum mechanics, quantum cryptography, you're talking about information theoretics. And when you talk about classical encryption, we're talking about computational theory, right? So how much computational power do you have? Now, computational power is not going to do anything to quantum mechanics based encryption, right? So you have to attack it from a different way, but you can attack it.
And Amy, you're about to say something, or?
I think that this really highlights this concept, and I really wish Conrad was here. I've been working with him for a while, and he definitely states it very eloquently, is we have to move, and I've heard this mentioned on some of the other panels as well, into the operationalization of encryption, which I just totally messed up, our agility in this area. The bottom line is we can't look at, we're going to have the same encryption standards for the next 30 years. And if you look at what NIST is rolling out in the algorithms, there's multiple algorithms. We have to look at the right places for those. So I think looking at where we've been able to say encryption is static for the most part, that's no longer going to be the case. And we're really going to have to start looking at things from different perspectives on this. And so lots of good points. It's not just one technology at this point, which is why this is kind of like the quantum and how it interacts with other things. If you're not looking at machine learning, you're not looking at AI, you're not looking at the holistic environment. And it's really, you know, the importance of not having those silos, as mentioned, like you're having the cryptographers talk to the cybersecurity people, talk to the engineers. Because, I mean, what's super interesting is when you look at most hacks today, it still happens by phishing, right? It's like, what, 80-something% of hacks still happen by phishing. But then if you look at some of the other hacks that's going on and you look at like the really interesting ones, right? The ones like where you're like, well, how did that happen? And you look at like where they used the smart thermometer of a fish tank to break into the whaling, you know, information in one of the casinos in Vegas. And you're suddenly like, wait, but they got in through a thermometer, right? That's the kind of attacks that I think are going to become more common in the future. And also looking at the attacks that super vulnerable in the military, that as we're talking about aircraft, when you look at the Navy and you're looking, you know, at ships and aircraft carriers, et cetera, is the components now, everything is dependent on technology. There are so few things anymore that we have that exist outside of having technology, and then more and more this technology is integrated across the internet, and it's been designed for speed and ease of use. It's not designed with security. And so we have to kind of go back to those fundamental principles and the basics on one hand, but on the other hand, considering very far out, like it's not science fiction now, it's science reality.
Michael, you mentioned quantum key distribution, and you're, I believe, doing some work there at the Air Force Research Labs on communications. And so how can quantum technology enhance secure data transmission?
Right. So yeah, you know, going back to you know, what Robert said, he did a great job talking about QKD and how it's not, you know, impervious to attacks, and it can certainly be broken. If you look at what NSA has out on their web pages in the public domain, certainly lists it, you know, the issues that are out there, and Robert did a great job with that. So in the Air Force, we're not, you know, to be clear, not doing any research and really not pursuing any work in QKD. There's just a lot of reasons why we wouldn't do that. But we're looking at the next step, right? And the next step is what I had kind of talked about, quantum entanglement distribution, what Einstein called spooky action at a distance, or you have one particle here. What you do here will affect another particle there. Always misconceptions about that. People think, well, it's faster than light communications. It's not. They put that to rest right now. You're not breaking the rules of physics. But what we are looking at is, you know, what kind of protocols can you put on that to then be able to securely transmit information in the quantum domain. So it's not going to be fast, you know, we're not going to go at internet speeds, gigabit speeds, but it will give you security, most likely at a lower data transmission piece. And then, yeah, I would also like to add too, you know, one of the things when we talk about, you know, I love this whole discussion about it's all the pieces coming together though too, but I think we also do have to be careful though when we start talking AI, generative AI, and quantum together, right? It's, think about the old chocolate and peanut butter thing together. Just because you smash them together doesn't mean you get that perfect Reese's peanut butter cup. And you know, you're not going to change Shor's algorithm by adding AI, and you're still going to need millions upon millions of qubits to be able to do that. So it's going to take some time to get there, to get a cryptographically relevant quantum computer. Where I do think AI is going to help, though, could be in the design of those qubits, the design of the systems, how you scale those systems up. So I think we just have to be careful as well as to not overhype putting two really overhyped technologies together as well.
Okay. One issue I'd like to touch upon is the workforce, because we always hear about, you know, the cybersecurity talent. You know, it's just a shortage, and now you have quantum, you know, computing. How are you going to get the, you know, the right people in, you know, place to be able to protect us with, you know, quantum coming?
Right. So yeah, I'll take a shot at this one from the Air Force perspective. And it was mentioned earlier this morning. I really like them. You know, start folks young, internship programs. Right, get them hooked on early. What we was just talking at lunch too about. You know, one of the things we do in the Air Force to attract and retain talent is our mission space, right? We have, you know, we're protecting national security, working in national security, working on really hard but very critical problems, right? But it's not a profit margin; it's saving lives problem. So you know, you have the sense of mission. You bring folks in early, even if they're not, you know, PhD quantum physicists, you can train them. You know, I love the term quantum engineering. I'm an engineer, so that's why I love that joke earlier. So, you know, I think, you know, there's all aspects, and as Yakov showed in his keynote this morning, right, you have that kind of winding road. You need things like technicians, you need quantum engineers, you need the PhD physicists, because you're always going to need to do that R&D. But it's bringing that whole ecosystem together, and definitely a lot, you know, internships, advanced education programs, and really getting quantum smart is what our workforce needs, but also pulling in the cyber aspect as well, right? There's a lot of technologies that we do need to bring together.
Okay. Sherry, do you have something to add?
Couple of things. One, on the Marine Corps side, we have something called Task Force Network Modernization, and that's modernizing the network to 2030 and beyond. In one of those, one of the task groups is talent management. And the reason I highlight that is both Marines and civilians are getting modernized in terms of talent. So everybody probably heard of every Marine is a rifleman. We're going to change that, or we're going to modify that a little bit. Every Marine is also a technologist and integrator too, because every single thing that they touch, right, whether it be that small screen or something on an aircraft or on a carrier or in space, they're touching technology, right? Or they might have wearables too that are monitoring their, you know, blood glucose or some kind of vitals, right? So every single thing, and they need to be able to know how to use that. And what I say is now, if we're moving to quantum computing and quantum technology, quantum cryptography, what is the cybersecurity behind that too, right? And Amy mentioned already, we are already going to assume compromise. So don't trust your stuff until you can verify and verify and verify again and again, because now you go through zero trust principles too, right? So, and then from the AI perspective, it's the ethical AI. What should be done, what shouldn't be done, depends on who you ask, right? The adversarial AI, what can be done against you and how much harm can be done. And then to the nostalgia algorithm, I got to go back to that again, sorry, is now 2024 is an inflection point, right? Just like 1980s, we look at 2024 and go up 25 years, right? And say, what do we do today to prepare us for 2040, 2050, 2060, and do we do that in the right time frame today? And did we make the right decisions, whether it be industry or academia and government as a whole too, right? If we don't, we have a small time frame, right? Because otherwise we're going to fall behind, and then now you have tech debt. Got to play catch up. So it's a problem that we can cope with today, but the longer that we wait, the longer the more problems and more issues we're going to have down the pipeline too, right? Especially if we're still working on, you know, flip phones versus smartphones, right? We're already behind the curve, so we don't want to do that and get ahead of it. So that the better thing would be in 2024, let's get to that next level and re-architect the entire baseline, whether it be hardware or software, to be compliant with this.
So,
yes.
I see that there is a critical shortfall for the required workforce to make this migration successful. And what I mean by that is, right now we have classical algorithms in place. The algorithms that are going to be standardized are not classical. They're different in a lot of ways. So we need people who can understand the classical algorithms. We need people who can understand the new algorithms, which there are very few on the planet that do. They're totally different architecture. So we need both, because there may be a period of time in which we'll have to continue to use classical encryption with post-quantum. So we need people who understand both. In addition to that, we're going to need people who understand quantum algorithms, quantum mechanics. We're going to need people who understand artificial intelligence and how all of these, and cybersecurity, how all of these relate together. I taught undergrad courses in cybersecurity, and I was surprised that they didn't have any understanding of cryptography. That has to change. We need to incorporate all of these topics in everything from cybersecurity certifications. We need to start looking at high schools, undergrad curriculum. We have to come together, academia, private industry, the government. I see that there's going to be a need for partnership to really develop the workforce necessary. It doesn't exist right now. It just doesn't. And it could be a potential national security issue if we don't.
So I think amazing points. And one thing I would highlight, if you have not read this administration's cyber workforce strategy, like definitely take that out and take a look at it, cyber workforce and education strategy, because we're highlighting that as, you know, that's the future. Every American, every citizen has to have some understanding of technologies, as what's really been highlighted. But if you also haven't read it yet, super encourage you to read China's cyber workforce and education strategy, because what you're going to see is there's definitely people who are thinking about this outside this room. And we definitely need to be aware of what others are doing in this space. It's definitely been highlighted that China is spending the most money in this space right now, and it's super scary. Another thing I want to highlight, though, is don't discount anyone in the room. If you are familiar with the history of cryptography at all, definitely take a trip up to the Fort Meade Museum and take a look at that. And there was an opportunity back around World War II where Hedy Lamarr, some of you may know this story, had a brilliant idea of frequency hopping. And she was told, don't worry about it, Hedy, you just look pretty and sell war bonds. So we had this wonderful opportunity to look at frequency happening significantly before it actually became revolutionized and real, because we discounted somebody in the room. And at this point, we cannot afford to discount anyone. And sometimes the craziest ideas are the ideas that work. And I think it's super important that we encourage that creativity, especially among the youth and kids today, that we bring them up in a society that encourages failure, because we learn from our failure. We learn very quickly. If you've watched the Marshmallow Task where the kids build towers, they actually build better than CEOs and other groups of people because they are willing to experiment. And we absolutely have to get to the point of being willing to experiment and just do not discount anyone at the table for their ideas.
Tom, do we have time for questions? I see we're... Okay. Oh, okay. Okay. Okay, great.
All right. Yes, you can. Just announce who you are and who you're with.
Hi, Sandy Mestry with Anakim Consulting, and thank you. It's been a fantastic panel, actually a fantastic day. So we're talking about these priorities and where we need to be and how we're going to know how to get there. I'm going to bring up that word budget. So there's so many competing priorities. Is how are you all within your respective agencies? How is that working? Because this is not the only, you have a lot of them. How are you working with the budget? How does that work with you?
Two things, priorities and partnerships, right? The first one is, how important is it? If someone thinks, having a meal is important versus doing something, needs, wants, and desires, let's say that. What is your main necessity? And then what's your additional requirement? Okay, I'd like fancier lights. Yeah, that's a want. Or a desire would be, okay, I'll go whatever, some nice shades, and I got to change the totality of the room or something, right? But the basics, if we can underline into, well, you got to change coaxial cable to fiber optic cable, right? That's the basics of the nostalgia piece, right? If we can figure out that is, post-computing cryptology and post-quantum computing, we got to put that as a priority, and that's a need, right? Then you can budget for that too, right? And then the second piece of the budget, yes, I agree. It might not all add up, right? All the ones and twos might not add up to the three, right? That's where we leverage each other, right? And I got good panel members here because now I can leverage industry and I can leverage other government partners, right? But then I also can leverage academia partners too, and the larger, technologists and the larger brain power that's out there too, right? So in that, hopefully we can gain cost sharing and cost efficiency too. So now we look at the entire paradigm of it. So hopefully that answered part of the question.
One more?
Dr. Watron, Department of Air Force, Chief Cybersecurity, Quantum, and Cognitive Information Services Architect. My question is, as we start talking about the need to integrate these different modalities with Title 10, Title 50, Title 18, Title 32, and Title 48, all of these technologies are obliterated, if you think about it, by this cross pattern of cyber modality of title authorities. How does the panel believe that we're going to do all these things when we can't get everybody to agree? Who's on first, what's on second, and who's going to go to third?
No one wants to take it?
I think that that's a supposition that it's going to work. And I just said I embrace failure. So I think that that's an important technique that you have to realize is the only way to get things to work is for people to agree on it. Because in the end, as much as we talk about AI is not replacing humans, and the human ego is a dangerous thing. So I think in the end, what makes it work is we have adversaries that we're aware of. And if you look at times when mankind has come together or humankind has come together to create great things, it is under adverse circumstances, and that will be the driver.
Yeah, I completely agree with that. I think, you have to start somewhere, you have to jump in, and you just have to figure it out, right? The next war, certainly for us, is going to be, it's going to be joint, it's going to be with coalition partners, it's going to involve all sorts of partners. So you have to figure it out, and we can't wait to figure it out either until it's too late.
Okay, it seems as though that there's a greater need for awareness, and there's also a greater need for collaboration. If there's one thing that you'd like the audience to take away, from this discussion, what would it be? I could start with you, Michael.
Sure. So yeah, something I hadn't talked about and it hit me. A great resource is quantum.gov, so put out by OSTP in the National Quantum Coordination Office. Lots of great resources there on our national quantum strategy, our workforce strategy in quantum networking, international partnerships, lots of great resources out there as well. And then encourage folks to read NSM 10, National Security Memorandum 10 from May 22, which really outlines, from the president, the executive office, priorities for post-quantum cryptography as well as quantum.
Amy?
Just want to highlight again, if you have not had a chance to sign up for the ATARC Quantum Group or the ATARC Zero Trust groups, we are working on these things in a government, industry, academia, research, partnerships areas, because in the end, no one can do this alone. It takes all of us working together and just recognizing these are the wicked hard problems out there, right? But when you can work with a group of people on this, like I was working with some of my ATARC members until like 5:30 on Friday before the holiday, and it was fun. And I was like, oh yeah, we should probably go, But in the end, those problems that are hard, those are the fun problems that you spend time doing, that you enjoy. And so definitely realize when you're struggling that you are not alone.
Okay. This is just a classical evolution of technology, right? Technology has matured, right? 1960s, 70s, 80s. We're into 2024. It's going to keep evolving. We just have to keep pace with it. And then the other part is we need to be able to leverage partnerships, right? Whether it be the partnerships here, but there's partnerships externally that we all can resource and use too, right? And it's got to come back into the government, into the large government, and then figure out between all the title authorities that was mentioned, right? How do we get past that, right? At the end of the day, the mission has to continue. Whatever that mission is for whatever government organization, it is to serve the public, serve the people. We have to be able to do that. And so the entirety is just continual pushing through, whether it be talent management or whether it be awareness, hardware, software, all of these things. And it's post-computing, then after that, it's going to be post-computing too, right? So we just got to be aware of it and get ahead of it, right? Go past the horizon. Thank you.
I just like to say that this migration it's going to take a long time. So once NIST announced the new standards, there's processes you have to go through. So for example, if you want to deal with the US government, you have to be certified, you have to get your products certified, whether we're talking about libraries, modules, hardware, software, has to go through a process to get certified to say that this is safe to be within a government space. That's going to take time. We don't have enough labs at the moment to be able to handle this massive rush for the new standards and certification. Finding the people to get this done. Yeah, well, we have new standards and we're ready to go, but who's out there that can do this? Who has the background? Who has the expertise? So I would say that we can't wait and say, you know, we'll get to this later. I've got something else I need to take care of. It's going to take planning and strategy that needs to take place now. Anything you do after that is you're late.
Well, thank you. Thank you, Michael, Amy, Sherry, and Robert, with the nice tie there.
Great panel, Rutrell. Now we have a super panel coming up. I just wanted to get a couple of announcements out of the way. Two big things happened today. One is my friend Peter Layton had a birthday. I think he's 49 again. No, it's a critical milestone for him. I won't betray his age. He's older than me and I'm 56. So buy him a beer or something. I think we didn't have a birthday cake. Sorry. I didn't know about it till a few hours ago. But another announcement we have is, I didn't announce, but we have Ross Ford from CISA is leaving government. This was his last panel at CISA. And what a guy, and what a contributor to this community. And thank you for being with us. And I heard there's a party for him coming up, and I'm sure we'll be seeing Ross around the neighborhood, but we're going to miss him in government. But anyway, nobody died. It's okay. He's going to still be with us. Next, let's get Alexandra and her panel up again. Alexandra's coming back for the final one of the day. I think we barely have enough chairs, so it's going to be a rousing finish to the day. Right?
Okay, I don't know about rousing. That's a little hyperbolic, but we're gonna try to pump it up a little. Could you restart the clock? Oh, okay. Okay. Okay, are we all here? All right, cool. Hi, everyone. All right, we rallied. We're back. We're gonna close out the day. You know, we've done so much discussion about application, about the need for collaboration. I mean, workforce. It almost feels like there is what's left to discuss, and that'll be our challenge, I think. But I have a really competitive panel. These guys they made me work to do my homework and make sure I could navigate all of their expertise and talents appropriately. So we are going to conclude the day by bridging the gap between science fiction and reality regarding quantum use cases. And ideally, again, we do want to keep everything into a federal perspective here. But our private sector friends are always, we're always interested to know what you guys are doing too. So with that, I would like I'll introduce all of my panelists. but I actually kind of were in flux with a few of them. So I'm going to ask all of them to maybe self-introduce and talk about how they work with quantum physics and technology in their day-to-day. So maybe kicking it off could be Dr. Davide Venturelli. Yeah, did I do that right?
Oh,
Yeah.
all right. Davide Venturelli. I'm working at the University Space Research Association, which is a research institution primarily working for NASA, but not only, very active in the space and aerospace sector. I've been one of the first members of the Quantum Artificial Intelligence Laboratory at NASA Ames in California, which is the agency's hub for applied research in quantum algorithms. So I've been involved a lot in key research projects from the NASA side, but also as part of test and evaluation team of DARPA projects, or as a performer, principal investigators in DARPA projects, all for applied use of quantum algorithms in conjunction with hardware. And I used a variety of hardware devices from superconductors and ion traps and the likes for trying to invent algorithms that could teach us something about quantum advantage. So, and I'm a physicist.
I'm Peter Brereton, so I also represent NASA, but I come from NASA Goddard Space Flight Center, so a little closer than Ames, just up the road. I run Goddard's new quantum sensing and quantum engineering laboratory, and so I'm kind of focused on the hardware side. We develop primarily cold atom based sensors, so laser-cooled sensors for Earth science applications, planetary science, as well as navigation and timing for deep space navigation.
Hi, everybody. My name is Catherine Potts. I work at D-Wave, who has a table over there if you want to come say hi. But we're a quantum computing company. We specialize in quantum annealers, which I'm sure you'll hear me talk about a bit during this panel. My background is in, actually, my degree is in applied mathematics with machine learning. So it's been really cool to hear people talk about workforce development, because I was one of those people that didn't really come from the physicist world, and I kind of found my way into quantum computing. So what I've been doing since I started in the quantum space is looking at building applications for quantum computers using different types of quantum computing systems. So gate-based quantum computers, photonic-based quantum computers, and then D-Wave's quantum annealers. And that's what I do now here at D-Wave, is I work with clients, public sector or private sector, to connect them with the technology and help them brainstorm how they can use quantum computing in what they're already doing today.
Hello, I'm Tyler Volkov. I'm a theorist in the theoretical division at Lano, and I'm a quantum information and algorithms researcher. I work in also quantum machine learning and quantum estimation and sensing. For the past 2 years, I worked on quantum radar and distributed quantum imaging. Besides scientific job at Lano, I also inform non-scientific divisions in Lano about bleeding edge development in quantum algorithms.
Hello, how's everybody doing? My name is Garfield Jones. I'm from the Cybersecurity Infrastructure Security Agency. I'm the Associate Chief for Strategic Technology, which means I mainly deal with emerging technology, trying to get our operational divisions to see that there are threats and there are good things that come out of emerging technologies. So my background's mainly been artificial intelligence and machine learning, and somehow got blessed with leading the quantum initiative at CISA. So that was you know, you need somebody to lead it. So it was kind of, I think I did one paper on photonics way back in the day, but had to get it back up to speed. And I guess my other link with physics is that my brother has a PhD in physics, so we go back and forth about being engineers and being physicists. You know, physicists are kind of crazy, and I mean, truly y'all are, but and then we've got the engineers who are logical thinkers. So we have a lot of good discussions on that. Thanks.
And I think we're going to turn to our virtual participant for a quick introduction, Dr. Tina Brower Thomas.
Yes, good afternoon. And my brother is in cybersecurity. So and I'm not a physicist, I'm a chemist. And don't forget, chemists are very much a part of the quantum workforce and initiatives and research and so forth. So as a quantum chemist, I have leadership roles in several quantum centers funded by National Science Foundation, Department of Defense, and Department of Energy. My background is in molecular self-assembly, and I started off in nanotechnology. That was a word that was around some moons ago. I hate to age myself, but you know, in that field, you're looking at behavior on the atomic scale, and that's what we have in common, obviously, with quantum materials. So I'm on the quantum materials side. I work in two-dimensional materials as well as growth of diamond for color centers as a source of a quantum bit. And I also have a lot of experience, particularly in workforce development and developing underrepresented minorities in STEM so that they can recognize themselves in a place in the quantum workforce. And I'm happy to be here.
All right. Well, thank you everyone for that introduction. And let's kick it off with something a little, you know, something that we're all interested in, right? The application component of quantum information sciences and technology. I love this panel in particular because we have a lot of researchers up here, and when I began kind of reporting and writing about quantum mechanics and technology, I really got into I got into it from much more of a physics background. I don't know if there really is a better way for anyone to really understand it up until that like very fundamental point. But maybe we can kick it off with our NASA friend here. And I really wanted to kind of talk to you in particular, Tyler, because you and I really bonded over like a no hype approach to quantum technologies. So maybe you can talk about some of the work that NASA is doing to actually distribute and leverage quantum use cases within the agency that are actually happening in real time and not complete hype.
Sure. Yeah, I think NASA in particular, and when we're talking about applications for quantum engineering, quantum information sciences in the public sector, NASA is in a very unique position as both an end user and a research organization for these technologies. As a public-facing science organization, one of our remits is to apply these the space environment, the aeronautic environment, and the sensors that go with it to problems that have public impact. And so when we're looking at the applications of quantum information sciences, the first thing NASA is focusing on in the near term are those unambiguous use cases that can fulfill particular science needs. And so NASA Goddard in particular has a large Earth science component. So Earth observation is a key observable. And so one of the unambiguous use cases is the utilization of cold atoms for measuring gravitational inertial accelerations. And so it's a as we heard, a wicked problem, how to get laser-cooled atoms into space, into the form factors that would enable these ultra-sensitive measurements. But as you know, it's a NASA scale problem, and so NASA as the agency then would integrate those sensors. And so we have that unambiguous use case that I think NASA is running towards. We've heard a lot about applications in the defense and security space. The nice thing about NASA going after those NASA scale unambiguous use cases is the technology chain to get to the exquisite sensitivities required for the measurement of water table changes at less than 1 centimeter from orbit. On the way there, we have to get through those sensitivities that would have applications in precision navigation and timing and GPS denied environments. And so, we can focus on the NASA scale problems, and on the way partner with industry, partner with the national security infrastructure to get those technologies on the way. So I think there's that part of it. The other side, and we've heard lots of engineering and physics jokes. Dr. Haydock might have made this joke. I wasn't here in the morning, but John Bell, who was the pioneering theoretical physicist who really gave us the means to measure entanglement, used to say, tongue-in-cheek, that he's a quantum engineer, but on Sundays he has principles. A tongue-in-cheek joke about the principles of quantum mechanics. But I think that's important for those of us who work in the big government science agencies, is that quantum mechanics has engineering applications, and those problems are extremely hard. But it also has open science questions, and NASA gets to go after those as well. So I think it's a good way to meet those use cases, which are hard, but also look to the future.
And that you mentioned timing, GPS. To me, that is sensor, correct?
Right. Yeah. And so the other unambiguous use case is optical atomic clocks. At prima facie, if we can measure frequencies at optical frequencies, you automatically get 3 to 5 orders of magnitude better than microwave clocks. And NASA needs these precision navigation timing, these clocks in space, so we can get to Mars. You have to have your own time on Mars. You have to have your own timing standard on the moon. The president just directed NASA to develop the lunar time scale. So that is another unambiguous use case. And so if we look at those near-term use cases, I think the technology chain required for some of the other use cases that we're talking about, synchronization, more forward-leaning kind of quantum 2.0 entanglement based sensing technologies, that will accelerate those developments.
Okay. Well, thank you, Peter, because I do know your name. But I mean, it took, while we have that unambiguous use case, that didn't happen overnight. It took us a while to get there, to arrive from point A to point B. So I'll actually turn to the real Tyler at Los Alamos. My apologies for the mix-up earlier.
That's okay.
A lot of the work that you're describing, frankly, I'm not very familiar with it. And mainly I refer to the imaging and radar work that you just talked about. Would you kind of give everyone here a bit of a rundown about what that really entails and how quantum mechanics factor into that?
Yeah, sure. So first, there's been a lot of talk today about problem with exponential quantum advantage, abelian hidden subgroup problem. This is not the sort of generic advantage that you can expect when dealing with quantum algorithms. Much more common is a polynomial advantage or even a constant advantage compared to classical algorithms. In my work in quantum radar, for instance, we explore distribution of entanglement prior to transmitting a signal to a target. And this allows, in the range of 3 to 6 decibels, advantage in the probability of error for detecting a target at a range of anywhere from scale of meters to kilometers. And the advantage doesn't arise from doing a complicated quantum algorithm, but actually just arises from having a long-lived distributed entanglement source, which is something that Dr. Haydock mentioned in the last session. So these I don't want to call them auxiliary quantum technologies, but these scientific basic quantum technologies that are necessary for advantages that are not just algorithmic, but also related to sensing and detection are important technological steps to get from the basic science to widespread application.
Yeah, funny enough, I mean, I've talked to everybody about this today, basically, and for as much traction and attention that quantum computing has, as it should, right? I mean, on a security and data privacy front, it certainly is better to, for once, be ahead of the curve. But we're not looking at a near-term application situation. So what you would call auxiliary, or what others may call auxiliary cases or use cases for quantum technology, I mean, those both, Tyler, sound infinitely more near-term and applicable and ready for scale before quantum computing.
Yeah, they're more limited, but the advantage is also, I should say they're more near-term, but the advantage is also limited. So we're not talking about, the best classical approach being exponentially worse than the quantum approach. So it's not as sexy as, the problems you learn about in Nielsen and Chuang's textbook, like Deutsch Jose, where an exponential the best classical algorithm is exponential, and the best quantum algorithm requires just a single query. It's too dramatic.
Well, we can pivot to what people like to talk about when they talk about quantum information sciences, which is the computing and algorithmic component. And everyone, we have covered today that estimations for a viable fault-tolerant quantum computer, which can actually execute some type of hack like that, it is, to be determined. But, let me turn to our CISA friend, Garfield. Perhaps you can talk to us a little bit about how, I mean, is your entire approach to quantum computing more preventative than anything?
I would say it's preventative in terms of, preparation, getting ready for it, making sure that the agencies and the components that are part of DHS are in the federal government are ready for what's coming. If you're not familiar with Moscow's timeline, look it up. That is one of the principal drivers in, I think, any federal space, is when we look at Moscow's timeline, we are a little bit behind on protecting our data. So that's our biggest thing now, is that, how do we slow I don't know if we can ever stop harvest now, decrypt later. But that's our principal goal, is to make sure that we get ahead of that, and that we're looking at technologies and the preparation activities that need to be in place. I mean, getting we're starting a roadmap of getting our risk assessments out, getting our inventory right, not just inventory of systems, but inventory of data, understanding that there's data that's very important and very sensitive to us, that has to be protected now. And, so we have to get that in the right place, not sending out, we talked some about zero trust, I think, in the last panel, and, it has to be zero trust and right now, because of the exfiltration that's going on with our data, and that there are adversaries within our system. So we are preparing and preventing in that sense, getting some policies in place, really getting the awareness of quantum. Not every C-suite executive understands the significance of quantum, which sometimes is an issue. But getting that awareness out is really helped to kind of kickstart that movement and prevent prevent and slow the harvest now, decrypt later.
So harvest now, decrypt later. I think everyone here is familiar with that, like, security talking point as the major, like, threat, absent of an actual machine, right? I mean, it's saying, okay, we can take our data, someone can take data, vulnerable data, And eventually, when we do have a fault-tolerant quantum computer ready to go, it will be able to potentially crack through Shor's algorithm, and bada bing, bada boom, you have a lot of data which is now exposed. So beyond, I guess what I'm asking, beyond the quantum computing threat, I mean, we do have sensor technology which is here already, and other kind of quantum communications which might be a bit more viable. Is CISA looking at securing any of those as well, or maybe applying some type of best practice approach to deploying those emerging technologies?
I think our main focus is still PQC, and will be PQC for the foreseeable future. QKD, I know a lot of folks are pushing QKD. There's some issues with that, as the Ford has pointed out. So we're not going to go against that. But there are going to be some other technologies. I think one technologies we're looking into now is using entanglement as far as communication. So I think there are some kind of bridge technologies, I guess, until PQC gets here. But our main focus is to get ready for PQC and not focus on the other technologies that could detract from that, because funds are very limited. I don't know if you guys have been with the federal government for a while, but you guys know it's pretty limited. So we have to kind of have that laser focus on getting what our primary goal is, which is PQC. The other technologies, I mean, we look at them, we see if there's a possibility of integration, but we're partnering with our industry folks, we're partnering with other government and FFRDCs to kind of evaluate these technologies, but we don't have a lot of leeway as far as pulling in a bunch of additional technologies.
Well, I'm glad you talked about industry partnerships. I mean, that has been a big CISA and Biden administration talking point for the emerging technology threats. So naturally, let me turn it to our sole private sector person here from D-Wave. I guess, you guys you have an annealing technology, hardware with a stacked software on top of, software stack on top of it. Given that you're you're in uncharted waters to some extent. I mean, how are you cooperating with some of the guidance that Garfield's agency and others would be putting out about ensuring that your technology is secure and working correctly?
Yeah. So, I mean, we're very aware of, the concerns folks have over quantum computing and also cloud computing, because that's how people access our systems today is through cloud API. We have a SOC 2 Type 2 compliance certification around that part of our system, and we're also looking at making sure we can deploy systems in areas that are, outside of the cloud if that's required. We have 3 systems right now around the globe, one in the United States, and then our headquarter or our R&D group up in Canada has systems available as well, and then we also have one in Germany. We've been working with governments, Australian DoD, other places internationally in their public sector to do things like last mile resupply, which we have a demo of over there, and TSA scheduling, all sorts of those types of applications. Again, because our quantum computer is specifically built for optimization problems, which is very different from a lot of the other technologies we've heard about today. And it's also very different from some of the quantum computers you may be used to as well, which I can talk a lot about, but I know we have other people to talk to. What I'll say is that D-Wave is quite unique in what they've built not only in terms of like the quantum computer itself, but also all of the infrastructure that they've set up and all of the research and development that we've put out. We have a massive string of papers about using our system for specific areas that show things like entanglement and things like that. We've been very dedicated in the space to support the science, as well as provide public companies and public sector groups access to our quantum computer so that they can use it in their areas.
Yeah. Well, let me turn to Davide. Am I saying that right? I feel a little worried about that. But as our, you've spent a lot of your career focusing on algorithmic work in particular regarding quantum computing and then technology. Maybe you can walk me through what, we know about zero trust, but what should security maybe look like moving forward and prior to us actually having something fault tolerant in the age where we have a lot of different private sector companies with a lot of different offerings? I don't think I'm alone here when it can get a little hairy and confusing when looking at, we have a pool of new startups, we have a lot of excited venture capitalists. What do you think the approach should be in terms of post-quantum cryptography, key distribution, and perhaps even the creation of new algorithms?
I think that our approach should not be driven by fear. As a community of researchers and innovators and of investment from both the government and from the private sector, the cryptographical use case is an interesting North Star for the field because we have a very clear understanding of the risk and the implications of what quantum technologies can do in this particular field. But the reality is we still don't know what quantum technology can offer to humanity in terms of quantum computing. And this is where physicists versus engineers comes, because physicists, engineer solves problems, physicist creates the problems to some extent for the engineers to solve. There's a lot of more questions to be asked than solutions to be implemented right now. So all this to say that I think everybody in this field has a vision, which I think it's 100% probably true, that many years from now, the entire IT infrastructure of everything will have some quantum technologies integrated, okay? They will be part of the way we process information. How do we get there? Well, we get there via applied research and fundamental research. Now, today's applied research is uncomfortable because we know that technology and computing specifically is not there yet to provide the advantages that we can have a glimpse of by theorems and theoretical research. But these are just, indications. The real value, hopefully, will come when the hardware is sufficiently usable, deployed, accessible, the ability of the practitioners, the researchers, the engineers, the newcomers, to play with that will be sufficiently user-friendly that we can devise hybrid complex algorithms that solves the real problem. And to get there, we can't just wait for next generation of computer until it's good enough and then start doing it. Like we need to co-design by trying to solve real world problems, even if we know that we're going to fail until the technology is there to support our ambitions and until we discover the principles to make it happen. And this is an interesting game. It's extremely rewarding from a scientific and technical perspective. And it is a little bit uncomfortable because we know we're set to fail until the technology is there. Mm-hmm. But it's a journey and it's noble, and it's important that the government keeps the lights on, because if business doesn't draw value immediately, then it's for the government to make sure that we keep the leadership that the United States have right now on the subject. And so I wouldn't use the fear of, oh my God, everything will collapse because of cryptography being vulnerable. I will really try to use the carrot of saying, we have an advantage right now, let's keep it on, and it's unquestionable that this will pay off eventually. So we just need to keep doing this.
So absent, a fault-tolerant quantum computer, absent some of the hardware that we're going to need, as well as the software, someone brought up to me a quantum-enhanced machine learning algorithm, and I'm not quite familiar with that, but I think it is self-explanatory. Do you find that being able to work with that initially might help us shed light and understand more things as users about the potential future technology we're looking at, which could be quantum enabled?
I think Tyler might have also some technical opinion on that. But I like the quantum machine learning field because nobody understands anything. Okay? So it's a playground. We as, machine learning is changing the world, okay? And it's a new fundamental way of thinking. I've been trained model-based to invent algorithms carefully, and now many of the things that I've been trained to do can be replaced by a neural network, which is data-driven. I don't know how it works, okay? It just works, right? So what I find interesting is what happens when we do have quantum systems which are sufficiently programmable and reliable, and I have strong access to that. So where I can play the game of creating hybrid quantum neural networks and then discovering by trial and error what works and what not. And then carefully understand whether if I see an advantage at application scale, I don't need the theorem that will tell me that I have an exponential advantage. Right? As long as I can discover it, and most of the machine learning systems employed in industry today, we still don't know how they work, but they do work. Okay, I mean, ChatGPT, we don't know exactly the power of things, but we know it's impressive. But of course, there are technical issues, and that's why I refer to Tyler, because I know Lionel is at the forefront of understanding the technical issues of quantum neural networks. So.
Tyler, you want to take it away? You have anything to add?
Yeah, sure. I should say that in 2015, I remember having a lot of discussions with my college roommate and grad school roommate, John Schulman, who went on to be a co-founder at OpenAI. And John kept talking about these Markov chain models, and he was coding up what became OpenAI Gym, these sets of robotics Python functions. And I just thought, he knew a lot about quantum actually, and I just thought, quantum is more interesting. Don't you miss like all this interesting math? And he said, not really. I'm interested in understanding why this code that I'm writing works so well. It was very practical, and at the time, I didn't think it was impressive. Now I think it's very impressive. But yeah, what I want to say about specifically about quantum machine learning is that quantum algorithms are good, particularly good for quantum simulation and for analyzing materials and devices that have quantum properties. Okay, they can be applied to classical problems, but they're especially useful for quantum materials and quantum devices. And similarly, or I should say analogously, quantum machine learning algorithms are natively good for learning materials or devices with quantum properties. And I want to mention that basically the analogy is that classical neural networks, work by having parameterized nonlinear functions, and quantum neural networks work by having parameterized quantum circuits. And you train the quantum circuits similar to how you train the classical neural networks. And there are the general classes of problems where this is going to be useful are things like classification of quantum data, characterization and verification of quantum systems, whether you have entanglement or whether you don't, whether some observables take some value or some value epsilon close to that value. And they sound like intrinsically quantum problems and far from applications. At LANL, after the the theory behind the quantum neural networks was developed in earnest from 2018 to 2022, scientists quickly began to find applications for these quantum machine learning algorithms, including F-electron chemistry and material discovery, which is relevant in clean energy, scattering cross-sections for certain chemical reactions that Lionel's interested in, and being able to efficiently prepare quantum states using quantum circuits that people didn't know about. So I'm reminded of the story of J. Robert Schrieffer on the New York subway, thinking of the Bardeen-Cooper-Schrieffer wave function that describes the superconducting state. Okay, he had to think about all these experimental papers that he read, and in some unspeakable stroke of genius writes down this wave function that he won a Nobel Prize for. Yeah, quantum machine learning is giving us a systematic way to do this by coming up with ansatsa, or predefined sets of quantum circuits that once we train the parameters, output quantum states that have the properties that we're looking for in certain experiments. And so that stroke of genius is a little bit less necessary.
Must be nice to have a stroke of genius like that. God. Oh, I can't do that. But while you talked about material science and potential applications there, I do want to rope in Tina on that in particular. I know that she and I had talked pretty extensively during our prep meeting about her background and how it does shape her approach to the need for input materials for quantum research platforms. And I found that really interesting. I don't know a lot about that. So, Tina, would you mind talking maybe a little bit about that and how that can contribute to continued innovation in the research sphere?
Yeah, so one limiting factor for sure in in moving ahead in applications of quantum is in the platforms themselves that bring about the utilization of quantum properties for example, quantum sensing and quantum information science. I hope you can hear me okay. I should apologize. I'm doing this on the road and I'm in a coffee shop and it's very loud for me, but and there seems to be a delay, but I hope you can hear me okay. Can you just raise your hand and tell me, someone give me an indication that you can hear me okay?
We're hanging in there. You're doing outreach. I mean, you're
Okay, all
talking
right.
about this in a coffee shop.
Right. So, but you know, and of course, quantum materials are very important and necessary. The research in the area is very necessary. It's also very expensive. I know. And so, I want to just put a plug in for the idea of cooperation between industry, academia, and government labs. I think that's really essential, and particularly for workforce development. Many things have been pointed out in terms of changes or improvements necessary for algorithms, improvements necessary for quantum safe cryptography, and so forth. But I just want to say that we see that as a threat, but in my mind's eye, the bigger threat is workforce development. So to whatever extent that we can make these improvements, if we don't bring along the workforce, to me, that's the noble cause that we should be considering as well. Because if we don't bring with us a workforce that can actually understand how these things could be applicable, useful, and also have a broad range of people that can contribute to the development, I think that is also a huge threat that we should consider. So I just wanted to make that point. And in terms of physicists versus engineers and chemists, you know, I love the simulation. Hoorah for simulation, but ultimately you need a chemist to improve coherence and to get you that pure trapped ion or photonic system. So let's not underestimate the role of material scientists and chemists in this quantum journey that we're talking about.
Yeah, great point. I didn't realize until today that y'all are ready to fight each other. Like engineers, chemists. I thought you guys were y'all spoke the same language, but I'm apparently completely incorrect about that.
Well, not completely incorrect, but I will say, the idea of transdisciplinary research or multidisciplinary research and the idea of I'm sorry, I hear feedback, so I don't know if you heard that. But anyway, all those ideas are very important because we can't work in a vacuum. Uh, if I can't get you a spin qubit that's reliable, your algorithm is not going to work. So we all have to work together.
Well, transdisciplinary research is actually a pretty good topic that I don't think we've really touched on today in terms of the collaborative effort, right? Peter, maybe at NASA, I mean, you guys do everything over there pretty much, right? Like, can you tell me a little bit about the transdisciplinary collaboration that you might have, at least maybe both interagency and then in the federal government writ large?
Yeah, I think, well, the comments about budget mean NASA can't and doesn't do everything. So,
yeah.
So that this, especially in this space, where the use cases are ambiguous and there are a lot of them and they require a lot of funding and effort, is being able to so NASA kind of has the double-headed mission of cutting metal today, getting sensors in space that work and provide the world with the data that NASA brings down. But also NASA has the benefit of doing things over decades. And so being able to invest in industrial partners through the SBIR, STTR process to get these small businesses that are spinning out of these research groups funded to provide the hardware, provide the research. NASA collaborates across academia. Last year we funded through the Space Technology Research Grant, we funded a cross-disciplinary research institute based out of the University of Texas at Austin Center for Space Research, I think called the Quantum Pathways Institute. But that particular institute really is a model. It's led by a space scientist developing the earth science engineering for climate sensors, but it partners with AMO physicists, electrical engineers, developing the next generation atomic sensors, the photonic integrated circuits that could get those systems out. And so an integrated system like that, it really falls within NASA's sphere. But I want to highlight that there are, when we talk about budgetary issues and cross-disciplinary efforts, one of the big ones that comes to mind for me is exactly what Tina was talking about. We are literally in the vacuum tube era, at least for atomic sensors. We are building vacuum systems to send to space. We need the massive investment in materials discovery to get quantum materials at scale and viable for these algorithms that are being developed to unlock the scalability and the availability of these technologies. And that can't be done by NASA, but I think it's a whole of government investment there with, you look at CHIPS Act, you looked at other investment priorities. That, I think, for me, falls very high on the public sector responsibility to get these technologies matured.
All right, I'm hearing one common theme, and I just kind of want to do it for the fun of it. But all right, on the panel, everybody, raise your hand if you want more money. All right, so it's never the answer, but it's never the wrong answer either, right? More money. Yeah, I guess maybe on the private sector front, I mean, money, you guys are more venture funded. Does D-Wave do a lot of partnerships with federal agencies or collaborations with federal agencies to maybe achieve some of these, gaps in innovation and research?
Yeah. We do partnerships. Typically that's done more at, a university level, but it has been done. We have worked with folks with NASA before. We've worked with folks in LANL before, and the other national laboratories collaboratively to further the science. We're always looking for more. Yeah. And we're always looking to kind of support those efforts. The core science, but then also, research into where the systems can be used today, because that's what the majority of our client base is doing. They're not necessarily waiting for a large, like, now quantum is going to take over in this space to get started. We have folks that are using quantum systems in production now to do things like employee scheduling, to do things like optimizing resources at the Port of LA. Yeah, that was an interesting, really cool use case. Basically, we were able to help improve flow of goods through the port by 60%, which is amazing. Where was I going with this? All of these things kind of come in together. So you have to have these collaborations between hardware groups, the scientists working on developing the science, and then also industry to kind of help fund all of those things together. Right now, D-Wave is a public company, so we are getting that sort of VC funding. I mean, don't quote me on this because I'm not the stock person. So we have that, but like without folks using our systems in production, without folks using our systems to do fundamental research, we don't get to build better systems, which is kind of one of the sticky points of where we are, I think, as an industry. We all really need to start working together to kind of help support each other, get more research funding, all of those sorts of things.
Yeah, I was having a conversation at my little table over there, and actually it was about NASA a little bit, because we were saying like, oh, NASA, you know, I wasn't alive for it, but I hear the space race, everyone really rallied around that. It was like a real morale boost, and you don't really have a lot of problems getting public approval for funding a lot of bigger ticket items. Occasionally in the public eye, you know, people like the idea of sending a man to the moon or to another planet. But if you bring up an idea like quantum technology, that sentiment can change. And it's because not many people have a real grasp of what you're really talking about. And I think everyone on the panel can definitely relate to that in terms of doing any type of outreach, or perhaps even asking for more funding from the federal government, that it's really hard to explain the importance of the work that you're doing. Tina, I think did you have a point you really wanted to jump in on there?
Yeah, you can tell I'm itching over here. I think one thing that I'm not sure many of us are thinking about is sort of reverse engineering the idea of what problem is going to be solved. So we have this idea of quantum adjacent jobs, and one of those could simply be, I shouldn't say simply actually, but could be, you know, how does the layperson find themselves in a discussion or with scientists about how it could be applicable to what they're interested in. So, you know, you have market development in terms of, I don't know, a car. Someone could talk to an engineer about what features they want in a car, but we don't have that same sense about talking to a broad audience of what they would want or what they would need. We talk to only scientists about the application of quantum. And I think that is a space that people aren't really thinking about. But I think that is also a space that you could get more support or more interest in what quantum can do. So, you know, and that can turn into sort of more of a business model. How are we really going to define what quantum is going to be used for? If we don't get a larger population of folks talking about that, then I think we can get stuck in the hype. And so I think we should be thinking about ways to get ahead of that.
Yeah, I'd like to, that's a good one. I think a lot of my panelists are going to have some opinions on that. Who wants to rattle one off?
I was just going to say, Tina, you're talking about my job. Because
we need more of you is what I'm saying. We need more people doing what you're doing.
I mean, I agree. You know, at D-Wave, we build the tools to kind of help people envision these sorts of things, but it's still not an easy conversation to have, because a lot of people hear quantum, especially in the business world, and first off, they don't understand what the word means, and then they get intimidated by the word. and by the science behind it. And it's really not, it doesn't have to be that way, because we have a lot of smart people, a lot of them in this room, that are helping build those tools so that it doesn't have to be as intimidating as it currently is right now.
Yeah, I mean, your background, you're a mathematician, which,
Exactly.
which is wildly impressive, and I wish I were you. However, you're not a physicist, right?
No.
And I mean, personally, you said you found your way here. Did you ever
That's true.
feel a little like, oh my God, what am I doing? What am I working with here?
For sure, yeah.
I'm sure, well, maybe the physicists felt that way too, to be honest, who knows, but.
Yeah, I started as an intern while I was doing my PhD at what I thought was going to be a software company, and it turned out it was a quantum computing software company. So so I came in, literally I had the job interview, and I didn't know what a quantum computer was when I had that job interview. So I had no idea what I was getting myself into. But what's cool about that is I found this totally amazing new technology that I didn't even know existed, that has changed in significant ways since when I started. I started in 2020 in the quantum computing space. The very first quantum computers were put onto the cloud around that time. And now we have systems all over the place, tons of different vendors in the quantum computing space that you can touch on the cloud. We're getting really close to the point where people have been talking about, seeing quantum advantage in the quantum computing space. That means things a little bit differently than in other modalities. So I don't want to get too much into that, but D-Wave is putting out papers that talk about that under peer review right now. It's just so cool to see how things have changed. And I look 5 years into the future, and I just see that continuing. So it's like, people don't know that they can get into this emerging tech and see it grow so quickly because we're not talking about it that way.
Yeah. Yeah, in D-Wave, you guys are, you have a quantum computer hooked up to a cloud, and then you're annealing, you're part of the commercial end of it.
Yes, yeah.
But then we have the national labs who spearhead a lot of the research, and then we have federal agencies who either are funding them, or maybe in SIS's case, they're working to kind of safeguard some adverse outcomes. And I can kind of get, how, the public is looking at, quantum technology, but there are many different veins that it can kind of go through. And so my question is, and maybe I can give this one to Davide or Peter, definitely Garfield. I kind of want to hear from all of you. How do you think it's best? Do you think it's kind of detrimental to a lot of innovation in the quantum technology realm to kind of have a fractured narrative about who is doing what and kind of who's helming innovation when it's coming from a few different spheres which do cooperation but could be doing more cooperation?
I just want to, before you go there, don't forget academia and fundamental and also technology driving. So just want to put that in the mix before we answer.
Thank you, Tina, and academia as well.
Well, I think USRA can represent as well academic standpoint. We're an association of 120 universities. That's our governance. And I can say that a plurality of approaches to the narrative, it's not necessarily negative as long as we keep some honesty in what we're talking about. I must say, I've been proven wrong multiple times with my academic hat. Sometimes, I'm a scientist. I have a sensitivity to BS, which is very, very, if somebody says something which is, misleading, I start, to be nervous. And I immediately want to call it out. At the same time, I have seen entrepreneurs proving me wrong, but deadly wrong on their ability to do something, and I lived in Silicon Valley for more than 10 years. So I known those people and said, yeah, sure, you can do that. Yeah, for sure. Yeah. No. Good luck. Damn, they did it and they made it. So I think everybody needs to humble down a bit. Everybody has a role to play, industry, academic, government. We're all up for the same journey. We should not mislead, overhype. but we should be optimistic. I said it before, this is a noble journey. I mean, we are coupling the fundamental physics principles that we know to the theory of information. And we are trying to get to the bottom of what is possible in sensing, communication, computing, in transduction, in all of this. This is great. This is cool. This is sick. We need to pursue it. And if there's a narrative of business and a narrative of academia, a narrative of government, a narrative of others, I mean, it's all good.
For the panelists who weren't here in Garfield, I'm going to get to you, but you should know that we kind of decided that we have to keep the lingo fresh and use words like cool and sick when describing quantum mechanics. So
Wow.
good luck.
Yeah, I lost my cool points a long time ago. So I don't know. I guess when you're looking at the different perspectives, it worries me a bit if we have too many different perspectives. One is because you get this, I guess you could say overhype. You know, there was a song back in the day called "Don't Believe the Hype," and it basically ends up like AI, right? You get a bunch of C-suite executives doing backflips down the hallway because they think they've broken AI or they've got AI in their system. It's crazy. So we definitely don't want that kind of, hype, fear, the fear mongering of AI to be in it. I mean, there is fear with quantum, yeah. But if we approach it the right way and we approach it, as a interdisciplinary, consolidated, I think, and get pointed in at least a few different directions, which is fine, but don't come and just all of a sudden bring this fear or some myth that you haven't proven, and then somebody's like, and then they propagate it at a conference saying, oh, quantum's going to kill us, and next thing you know, it's like, oh my God, we don't want quantum, and then we get Elon Musk and everybody else signing, little papers and documents. No, we've got to make sure that, as a community, that we go forward and we look to the academic organizations, we look to NIST, we look to all the EU standards and things like that. So we make sure that we're having more of a consolidated message versus a whole bunch of different factions that kind of bring more fear than they actually kind of push the technology forward. Sorry, I don't have any cool. I mean, oh, he used sexy, so I was going to use sexy.
God. All right. Well, actually, funny. That's a decent transition. Somebody asked me about ethics, in quantum technologies, and I had no idea what they were talking about. I mean, number one, why would I? I'm nothing. I'm literally the moderator, but I mean, when I'm looking at experts here, I mean, what are ethics in quantum information sciences to you? I mean, AI, it's pretty, I get it, right? That's an anthropomorphic kind of technology, and we're treating, we have an opportunity to kind of leverage it in very sensitive ways. But, it's like ethics in quantum, I don't really get that. But what they were really referring to was the democratization of knowledge, right? And the democratization of what maybe a private sector party knows, what we're doing in national labs, what academic research is looking at, and how important it is to actually to not gatekeep that, at least not nationally, at least not within the US domestically. And maybe, on the democratization of knowledge front, we could talk to Tyler a little bit about that from Los Alamos. Do you guys do a lot of, I don't know, in collaborations with other labs? You guys are a DOE-funded entity. Do you transition a lot of your work into other federal agency operations?
Yeah, Lano's part of a Quantum Science Center, which is one of the national quantum information science centers. The name center is misleading because it's not a center. It's a distributed collection of institutions, academic, private, and government, and all sorts of divisions at Lano participate in that knowledge transfer. There's a yearly meeting with a lot of scientific seminars on all sorts of basic science deliverables, and I think our private partners benefit a lot from that. And then we also get the opportunity to use their cool hardware that we don't develop on site. And so there's a synergy there. I think also, to my knowledge, all of the quantum information science centers have some kind of quantum summer school or some pipeline between academia and the laboratory. Well, yeah, and then, yeah, I should also say that there's, of course, quantum research at Los Alamos that is not democratized.
Yeah, it might have been a dumb question.
Well, it's not. No, it's not a dumb question, but I mean, that's important to take into account also.
Yeah, national security is important. Peter, would you like to tack onto that?
So I think if we come back to sensing, in some sense, there's a huge security implication with some of the algorithms that are being developed. But I think we have a unique opportunity. Any quantum success, I think, would a rising tide lifts all boats. The potential for a public-facing demonstration in the near term of a quantum technology making real discoveries, I think would impact the worldwide community. And NASA, by its nature, is collaborative. The Cold Atom Lab on the International Space Station right now is a close collaboration between NASA, JPL, and the German Space Agency, and is really open to worldwide scientists to operate. So I think there's certainly a space for understanding where to put those firewalls, but I don't think fear about use case or fear about maybe edge cases on security implications should paralyze us from cutting metal and getting systems into the field as soon as possible.
All right. Well, no fear is sort of the takeaway that I'm hearing from this panel, more or less. But I've been informed that I have gone firmly overtime, and I've kept all the panelists up here after hours. So I apologize, and thank you all for hanging in there with me. Do you want to do audience questions? Or, I don't know.
I think we got to get some folks out of here, but you're welcome.
Oh, well, bye.
We got one. Well, I'll have to go. Okay, we got one question.
Hi. Yeah, I'd like to find out what's your take on the effectiveness of the quantum radar against stealth?
Just a softball for you.
No, it's an important question. Things like jamming attacks and other adversarial approaches to disrupting radar systems have to be taken into account when you formulate the information theoretic setting for quantum radar. And that's not an easy thing to do. Mathematicians and physicists like to start with simplest possible descriptions of the problem and get things like lower bounds and theoretical limitations as cleanly as possible. Well, in reality, when you're considering what are the actual quantum advantages of radar, you have to consider these kind of adversarial aspects in a formal way. We take those things into account in doing the analyses.
Who wants to follow that question up? Now, this is great. Great panel. I noticed we had 6 PhDs up there. I think we had a total of 13 for the day, but great job moderating this panel, and great job by the panelists. Thank you.
Thank you, guys. Oh my God, all right, we did it. Go home.
Now I have about an hour keynote I'm going to give. No, I'm just kidding. Great day. I think we need to get a nap or something after this day. I learned a lot. Fantastic. Thank you all for coming. Thank you to our partners that participated in this. We have them up there. Yep, these are A lot of them market leaders, some are upstarts, a lot of media partners. Thank you all. Thank you to Carasoft. Hannah, why don't you come out for a second? She's like the Wizard of Oz. She's back here making things happen. Hey, yeah, come out a little bit more than that. There you go. Okay. Thank you to my staff, and everybody have a good rest of the day, and we're going to continue the collaboration in our working groups. Thank you all.